And welcome to the second day of the program review days in 2021. My name is Antonio Aguiló, and I am a project officer at the Clean Hydrogen Joint Undertaking, and I'm following here together with my colleagues our activities on a stationary application with fuel cells. Yesterday, you heard from us a summary of our activities, of our projects in this field, and for this morning, we have two exciting parallel sessions in which you will hear from a number of projects that we are supporting in this area. This session will look at a number of demonstration projects, deploying systems in operational environments or real installations, and immediately after these sessions, we will have another sessions looking at our research projects in this area. The following presentations will cover applications looking at the residential sector, power generation for remote applications, innovative power generation systems with solid oxide cells, and finally, power-to-power solutions in off-grid and isolated areas. We have 4 speakers for that. Now, I really invite the audience to use the Q&A button, the questions and answers button, to post any questions you may have. Please interact with us. It will make the session more dynamic, and I really hope that you enjoy this session. So without further delay, I'm very glad to give the floor to the first speaker, Mr. Gunter Grosch. He's product manager at Zenertech, and he will present the activities in the PACE project on behalf of the project consortium. PACE is looking at the demonstration of fuel cell systems for micro cogeneration applications, and we will hear on the progress today from Gunter. Gunter, the floor is yours.
Yes, thank you to Antonio, and thank you to the audience which are attending this room, and hopefully I can give you some information you're interested in. We talk today in my session about PACE, and I'm Gunter Grosch, working at Zenertech since 1988. Zenertech Kraft-Wärme Energiesysteme is a company that manufactures micro CHP. Our products are also well known as DADAX and offers matching system solutions for micro CHP products. We are part of the BDR Thermea Group. Next slide, please. Micro cogeneration with fuel cells. What's about and why? With fuel cells, you are heating and powering your home efficient and environmental friendly. This empowers consumers, supports the European energy transition, provides greater flexibility for the energy systems, fosters innovations and high-value jobs. Next, please. A number of projects like Calux, Ennefield, PACE, and the supporting funding programs as the KfW 433 shows us the history of the development of fuel cells. These projects are driving the fuel cells micro CHP closer to the mass market. The question is how to overcome the point of greatest risk in new products commercialization. Let's focus on PACE. What are the project targets? Targets are reduce cost and improve competitiveness, improve product performance, establish full cell micro CHP cogeneration as a standard technology, raise awareness on fuel cell micro cogeneration, demonstrate product readiness as a key component in the delivery of EU's energy goals. Next, please. Here we can see some details of PACE. PACE is a large-scale demonstration of micro CHP fuel cells. The project has been running since June 2016 with a budget of more than 90 million euro. The actual partners are BDR Thermea Group, which Zenertech is part of, Bosch, Cogen Europe, DTU, Element Energy, HSLU, Solid Power, Viessmann, and Hexis. Next, please. The different brands offer 2 fuel cell technologies, the solid oxide fuel cell technology and the proton exchange membrane fuel cell. in the range of 700 watts up to 1500 watts electrical power. The overview shows the quantities brought onto the European market by the individual brands, mainly in new or existing 1 or 2 family homes. Next, please. Since December 2016, the population of the fuel cells in Europe under PACE has increased. As the time shuttle here shows very clearly, up to nearly 2,000 units in October 2021. Next, please. Up to the first quarter of 2021, nearly 1,850 units had run for about 14.5 million operating hours and produced more than 15.7 million kilowatt hours electrical power, with an efficiency between 35 and 60% and an availability of 97 up to 99%. Next, please. The regulatory barrier working group identified these 5 key barriers to the promotion of the fuel cell micro CHP technology in Europe. Take in financial incentives with no common subsidy scheme across Europe, or the micro CHP is not considered eligible for existing subsidy schemes. For the electricity tariffs, exist different incentives in the countries. The process for reaching an agreement to export electricity is long and troublesome. The process for connecting units to the grid needs to be simplified, but evolving grid codes impact the confidence in the market. The potential to operate on green gases is unrecognized, and units are often unfairly penalized in regulations. In the unit labeling regulations, the technology is penalized. The regulation fails to recognize the energy efficiency. The recommendations of the working group are the standardization of regulation across Europe is essential to overcome barriers across all 5 pillars. Communication between states and the sharing of best practice examples will help to simplify the process for potential customers. Engaging potential customers and highlighting the advantages of this technology will help to encourage confidence in the market while regulations are being updated. Next slide, please. Let's have a look at the work package 4 of the PACE project. The challenge: identify additional income streams from the participants of micro CHP in grid service markets. Take advantage of micro CHP flexibility. Grid services analysis covered traditional markets, for example, the frequency balancing and emerging markets congestions. Also analyze hurdles, opportunities, readiness, develop roadmap and recommendations. The approach was model-based optimization, taking into account thermal storage, building thermal inertia, electricity demand, heat demand, literature review, and interviews. Considered mix of member states and regimes. For example, Eastern and Western Europe, spark spreads, generation mix. Next slide, please. Here are some outcomes in headlines. The greatest opportunity comes from maximizing self-consumption, up to 2,239 euros a year for 3 family houses. Up to 301 euro a year as additional income from frequency balancing. Grid reinforcement avoidance from demand side flexibility benefit of up to 500 euro per kilowatt. Widespread realization in 5 to 8 years with no intervention. Aggregation of more than 1,000 units required to make business case for small-scale flexibility. Integration in HAMS is best option. Single biggest hurdle for micro CHP is cost benefit for CapEx versus revenue per unit of flexibility. Next slide, please. The last slide shows us the achievements of some deliverables of the work package 4 in detail. This is the deliverable 4.3 is completed and also 4.5. And I pick only some achievements out. It's economic value of the full cell micro CHP participation in power and grid services markets, where we have completed economical value analysis for 3 countries, considered grid services and avoidance of grid extensions. Examined legal and commercial hurdles to participation in grid services markets. Here on 4.6, we have the final draft, which shows us a roadmap to capitalize and move further the potential of full cell micro CHP for demand response as part of a virtual power plant. Analyzed OEMs and aggregator perspectives, proposed generic steps for improving micro CHP participation in grid service markets. And the deliverable 4.5 completed the European Grid Service Market Symposium. We had a symposium in 2019 and 2020, where in scope of the work package 4. However, symposium was also held in 2021, creating an opportunity for further networking disseminations on PACE. Thank you for your attention. The last slide, yes.
Thank you. Thank you so much, Gunther. I mean, you've mentioned we have almost 2,000 units installed now in the project PACE, and you've shown 15 million operational hours, 60% power efficiencies, and up to 90% availability. I think this is good news and good progress. And maybe I just wanted to point out that the units that the project is installing now are already the 2nd generation of systems, meaning that the units have seen already improvements relative to this 1st generation. And I guess, of course, this is why this very good performance results. Then there is a question I wanted to ask you. With 2,000 units installed and many more in Germany, I understand Germany now has filed around 18,000 applications under the National Support Scheme, which is quite a big number of units. I wanted to know a bit more about the end users. I mean, who are installing these units? I'm thinking a bit on the profile of the buyer, of the end user, but also in terms of the type of households. I mean, what would you say, in your opinion, is the most suitable type of households to install these units?
Yeah, it's new houses and also residentials, which is 1 or 2 family homes. Also, light commercial homes are preferred to install a fuel cell unit. And when you look to the profile of the users of or the end customers, let's say it's a mix. The micro CHP at all is mostly used by good situated people which have a good income and let's say sometimes are very interested in new technologies. And it changes at the moment from our perspective, because you can also see, say, younger guys which are also interested because they want to change the, I think, the time. Let's take an e-mobile and let's have a better look on the environment. And therefore, what can I do for that? That's our reasons why they decide to come to a micro CHP unit or fuel cell unit. What is not so recognized mostly is the fact that at the moment units are driven with natural gas. And this hinders, as I have also given you in the presentation. And recognized is not that this technology is fully ready to do it with hydrogen. So the only thing we have to change is let's bring hydrogen to homes. Then it would be, I would say, explode the market.
Thank you. That's good that you point out, because there was a question on this direction on the forward compatibility with green hydrogen. So there is a question also asked by the audience about the units themselves. Do they integrate batteries, these units? I mean, in their systems?
Yeah, well, for sure, it depends on the system. On the PACE side, I take out my one because this is the one I know best. And for sure, with an energy manager, you can take batteries also into the system. You can make a complete solution, as you have seen in the first slide of our presentation, with photovoltaic on the roof, with a battery system in the cellar, and also a charging station for e-mobility. It doesn't matter, you have only to bring these systems together and manage the energy flows. Not only the electricity, but also the heat, which is the heat demand of the house. This is what we are trying to achieve with this new kind of technology.
Okay. Thank you. And the last question I wanted to bring to you, because I mean, eventually heating is of a local nature. I mean, it happens a lot of it in our cities. And there is a lot of debate, of course, on the back of the transport sector in terms of local air emissions that we have from transportation in cities. But there is an element as well of, okay, we do have boilers, we have gas boilers in cities. So what do fuel cells offer in this regard? If I'm thinking about NOx emissions, for instance, particulate matters, I mean, what do the fuel cells offer? Some advantages relative, for instance, to other conventional technologies?
Yes, for sure. The advantage is at all that with the fuel cell, we have a much more efficiency in the homes, and it's also ready, as I said, for the hydrogen future. Let's say also boilers will be ready for hydrogen future, but the possibility to do a co-generation of electricity and heat. This makes this technology unique to all the others, which all need input of electricity to work in the right way. And with micro CHP, you fulfill also the demand of the electricity in your own homes.
Thank you. And indeed, and I should say that they are not combustion devices. So eventually, I mean, if I could add, no, they are electrochemical devices. So say they don't really rely on combustion. So NOx emissions are as low as zero or very low, of course, or ultra low, depending on the chemistry. Thanks a lot, Gunther. I'm afraid I'm going to have to pass to the next presentation. Thank you very much again for a very nice insight on the progress of PACE. And I'm very happy to pass the floor now to Mr. Jari Kiviaho, Senior Principal Scientist at VTT on Smart Industry and Energy Systems. And Jari will present the progress of the RoRePower project to date. Jari, the floor is yours. Thank you.
Okay, thank you, Antonio, for your kind introduction. Like Antonio already mentioned, my name is Jari Kiviaho, and I'm coming from VTT, and VTT is Technical Research Center of Finland, and me personally and the VTT is coordinator of this project. Today I'm presenting the RoRePower project, and this project was initiated because of the call 2019, and the project started in the beginning of 2000. Project was initiated 2018, and the project was started 2019, and it will be a 5 years project. Total project budget is around 4 million euros, and the EU contribution is around 3 million euros. And currently we are pretty much in the halfway of the project, and implementation is around 60%. Next slide, please. Our consortium is small, but very nice consortium. We are having partners for 4 different countries and the 6 members. And from Finland, we are having a VTT, as I already mentioned, and the 3E Energy Oy. And from Germany, we are having a Sunfire and Sunfire Fuel Cells. And from Switzerland, European Fuel Cell Forum, and from Italy, Solid Power. So our consortium is containing stack and system manufacturers and also a research institute and the consultants. So I would like to say that this is very nice consortium. Next slide, please. The overall objective of this project is to develop and demonstrate solid oxide fuel cell system for power generation with harsh climate condition somewhere deep into forest or into high mountains. And here in this slide below, you can see very typical demonstration sites. First one in the left corner is demo site in very high mountains, very cold places. And the second picture in right corner is picture from Finland, where we are just deep in the forest, middle of nowhere. And these are the very typical demo site in our project. Next slide, please. And our primary market area or customers are gas and oil infrastructure and telecommunication towers in remote regions. And like I already mentioned, that our aim is to provide good technology, remote power generation is harsh climate condition from -40 up to +550 Celsius centigrade. And of course, whenever we are bringing new technology into the market, we are offering reliable and long lifetime of the systems. And of course, with the new technology, we are willing to increase the electrical efficiency and minimize the emissions and offering energy and carbon savings. And whenever we are talking about the new technologies, bringing new technology into the market, we are always talking about the cost. And our major aim is to reduce the total cost of the ownerships. That is very obvious target. And how we can get that target, which means that we are achieving cost reduction on both stack integration and the specific BOP component. And also we are putting effort to decrease maintenance cost of the systems and for the remote monitoring. And like I already mentioned many times, that because we are having a new product here, new kind of product here, we also want to create track record for market introduction, getting a good reputation for the new product. And always we are looking for the new customer groups. We are expanding our application and customer segments. As a summary, I can say that our SOFC technology here is very competitive with the conventional technologies. Our TCO emissions and maintenances are usually lower than the in the case of conventional technologies. Next slides, please. And then a few words about the project progress. I have chosen a few examples here. And the first one is how many units we have been installed. Our project target is to install 47 units. It sounds not so much if we are comparing the previous project where they are installing thousands of units. However, this is a very important target anyway. And currently, I mean, in this year, we have already installed 30. We have already installed, or installation process are running in the customer sites in the case of 30 units, and which is around 64% from the RoRePower targets. And most of them are in telecommunication sector so far. Rest of the 17 units will be installed before the end of next year. So we are pretty much on track in the case of installation units in the remote areas. And the next slide, please. And of course, harsh condition operation. Like I mentioned in the beginning, that our temperature range are very demanding. It's -40 to +50 Celsius centigrade. And starting system in those conditions and also operating in those conditions. In the case of +50 Celsius centigrade, I would like to say that it's piece of cake for our systems, because it can be reached very well with the good ventilation, and we have already done it. It's achieved during this project. In the case of cold climate, Sunfire fuel cells has demonstrated their system in -20 with the natural gas and -35 with propane. And Solid Power has demonstrated system in -20 with natural gas. However, I would like to mention here that operation between -40 and -20, it's not very critical, because whenever you are having a very good insulation with your systems, you can utilize the wastes coming from the fuel cell system and keep the cabinet temperature in very well nice range, and operation in very cold ambient atmosphere it's not a problem. It's also a piece of cake. Startup between -40 and -20. It can be taken care of by using a low temperature startup heater, which heat up the cabinet until the cabinet temperature is somewhere between -15 and -10 Celsius centigrade, and then fuel cell system can very easily start. So I would like to say that in our project we are also very good on track with this target, and our systems can very easily, not very easily, but can operate in the temperature range -40 to +50. Next slide, please. And of course, when we are talking about the cost reduction, which means that the maintenance frequency and maintenance duration, it's very important, and you can have a lot of savings there. And our project targets are for the maintenance frequency is 15 months, and for the maintenance duration, it's 4 hours. And our partners, Sunfire Fuel Cells, has demonstrated maintenance frequency 13.7 months, and the maintenance duration is 1 hour. In the case of Solid Power, maintenance frequency is 12 months, and the maintenance duration is 4 months. And here I would like to mention that probably this is enough from the practical point of view. I mean that 1 year maintenance frequency can be a very, very good maintenance frequency because of the, for example, weather condition and so on. So I would like to say that we are at least very close to reach this target, and perhaps we need to do some development work here also. It depends on what customer and OEMs want to do here. And the next slide, please. Risk, challenges, and lesson learned. Whenever you are working with the customers and negotiation with them with the contract, it's challenging to have a finally binding contract with the customers, and also the realization of the demo site is very challenging with the customers. And there's always some time restrictions, and to reach long enough demonstration time during the project, it's always challenging, because readiness of the production system, production lines, and system manufacturing in the project time frame can have may have some delays, and which then cause some pressure for having a long enough demonstration times. But in our case, it seems that we are still on track in that case. And of course, whenever we are talking about money, budget restriction, we always want to have more money to manufacture system and install system in customer sites. And then finally, a very good excuse, which it has been used many times already during this seminar. There is some delays caused by COVID-19, and that's the fact that because of the COVID, we have suffering some problem in building up production lines. So I would like to summarize somehow that RoRePower project is very challenging demonstration project, but it's moving all the time to right directions. Of course, this kind of demo project contains always some uncertainties, like all other projects do, but I'm very optimistic we can solve all kind of coming challenges, and finally we are having a very successful project. Next slide, please. Exploitation plan and expected result impacts. Our exploitation idea it's mainly generating business in coming generation of the products, and our exploitation happens by increasing sales volume and turnover, increasing number of jobs, and also synergies with other products, and then a strong collaboration with suppliers, component suppliers, and end users. Impact. In our proposal, we mentioned many impacts what we are going to achieve, and here I have just picked up 3 examples which we have already achieved. And the first one is just related to the component. Nearly all components for RoRePower units have been manufactured and sourced in Europe, which means that we have give our efforts and input to strengthening European value chain in the area of fuel cells. And RoRePower has also introduced new kind of technology for the niche market, like telecommunication and oil and gas sectors. And also I can mention here that the Sunfire Revolt units has provided the best-in-class electrical efficiency comparing to conventional technologies. And the next slide, please. I was believing that I can show you some very nice video here, which has been made by Sunfire, but unfortunately, from the technical reasons, because of some technical reasons and technical problems, I cannot show it right now to you. It's 2 minutes video. It's very nice video, and please, during the coffee break, go there and watch this video, and it's give you a good picture what we are doing in our RoRePower project, and you can find remote.sunfire.de. It's a very nice video. And the next slide, please. And here I just want to summarize that RoRePower is very much very well on the track, and I'm very optimistic that in the end of the project we will achieve all objectives. And so in this point I like to thank you everybody for your attention. Thank you.
Thank you. Thank you very much, Jari, for the presentation and the nice insight. I mean, it's very good to see, as you say, that progress is being done, 64% of the units either installed or under installation, and we're looking forward to see the results. I think it would be very nice to have next year the results of these units that have been recently installed. I wanted to ask you something in relation to the units themselves. Could you provide some information about the size of units that are being installed, and also so that the audience can also understand the alternative solutions that are displacing? I guess they are providing needs that nowadays are done by some type of technologies. So a bit on the size of the fuel cells being installed, what type of solutions they are displacing, if you could comment on that.
Okay, from the sorry. From the Sunfire fuel cell point of view, they are delivering 350 watt system and 850 watt systems, and in many cases those systems are integrated with solar or batteries, and with some kind of hybrid system, and the final structure and depend on very much on the customer demands. And in the case of solid power, they are delivering 1.5 kilowatt systems like in base project. what are the conventional technologies you was asking here? I think that I am not very familiar with that. What kind of technologies customers are used to use in their premises? Because I have in many cases, the sites where we are delivering our systems are confidential places, and we have coordinator is not having access for there. But I would very easily imagine that diesel generator and PV with batteries, that kind of systems, it's already there. And then this kind of solid oxide fuel cell system can provide more reliable and more efficient and more clean option there.
Mm-hmm. Thank you. And there is a question actually from the audience in the directions of why solid oxide fuel cells are selected, and the audience mentions why not PEM or other chemistries. And as a link question to that, it's this because of the total cost of ownership of the technology. Some audience says, is that because solid oxide fuel cells can reduce the waste heat, but others cannot? I don't know. What can you say on that?
Well, that's a very good question, and I am not so sure can I really give an answer which fulfill all requirements here. But one reason here is because of the waste heat coming from the solid oxide fuel cell. Like I mentioned, in very cold climate, I mean that the system is providing heat which can keep the cabinet warm and make possible to run system even in -40 Celsius centigrade ambient temperature. And second reason is that the efficiency of this kind of system is much better than the conventional technologies. And third one is the fuel what we can use here. It's natural gas or liquefied natural gas or propane, which means that this kind of fuel, solid oxide fuel cell, can use such a fuels if we are having, for example, PEM fuel cells there, which means that we must have a pure hydrogen, or the reforming process of natural gas propane. It's more challenging to produce pure hydrogen, which can be used in PEM fuel cells.
Thank you, Jari. And one question in the direction of how the project intends to reduce the capex and the opportunities for streamlining, if you want, the supply chains. If these units would have maybe common components, how does this, for instance, could be done? Reflecting a bit on the type of OEMs that the project may have, is that something that the project intends to do?
I am not absolutely right person to answer this kind of question, because the OEMs is having a much better view for that. But I think that for example, we are using already commercial component in which are suitable for the harsh conditions, which means that because those components are already commercial one, the price is also decreased in a certain level, because they have those components has been manufactured by using mass manufacturing production lines. And also one way to reduce the cost is some kind of common purchasing of the component. OEMs can have a collaboration when they are purchasing a component from the suppliers, and when the amount is higher, then you can also have some discount for the prices. But the final answer for the cost-related issue, I think that the companies like Sunfire Fuel Cells and Solid Power are more capable to give a final answer for that.
Thank you, Wes. Thank you, Jari. So thanks a lot for taking the questions and for the clear answers. So we now run out of time and we will have to move to the next presentation. So thank you very much. And I would like to pass the floor to Miss Ilaria Mirabelli. She works in High Gear. and she's taking part in the CH2P project, and she will be presenting to us the progress to date on this project. Ilaria, the floor is yours. Thank you so much.
Thank you, Antonio, for the nice introduction. And good morning to the audience. My name is Ilaria Mirabelli. I work for AGEA, and today I'm pleased to present to you the CH2P project on behalf of our coordinator, Luigi Crema, that could not attend this session. So let's start with some figure. Next slide, please. So the CH2P project is addressing the topic on cogeneration of hydrogen and electricity with a high temperature fuel cell. And from the call of 2018, is a 5-year project that is expected to end on April 2022 with an overall implementation stage about now 74%. We have a total budget of 6.8 million and a contribution from the HJU of around 4 million. Partners from 4 different EU countries are involved, including research center and the university, as FBK, DLR, and EPFL, but also company as AGEA, Solar Power Group, and Shell. Next slide, please. So what we aim for is to produce hydrogen at a quality level needed for hydrogen refueling station application at high efficiency and low carbon emission. And how we intend to do so is by constructing and validate a prototype able to cogenerate hydrogen, heat, and power by using solid oxide fuel cell fueled by methane-rich gases. Next slide, please. The main goal we focus on are the production of hydrogen and electricity in a more efficient way with respect to the conventional technology, but take into account also what are the needs for decentralized hydrogen production from the point of view of an hydrogen refilling station, and thus having as a target the purity level needed for automotive sector application, and also, let's say, looking at a flexible production capability and how then this could be achieved. Then, for instance, design a system that is able to operate in different modes, meaning a different output in terms of hydrogen and electricity produced, and also design a system based on the modularity concept that then can allow, let's say, a staged deployment of such infrastructure. And I would say also keeping an eye for future development on the possibility to include a grid stabilization service, for instance, in case of power peak demand in the grid, that then could be, let's say, covered by such a flexible power generation. Next slide, please. So then, how should look like a system with this feature? Well, CH2P system is designed considering what are the existing energy infrastructure and the available technology for energy conversion. So basically, it integrates the main sub-process involved in the hydrogen production. So from the feedstock conditioning and fuel processing to the conversion into power and hydrogen, see via the fuel cell technology, and then the further compression and hydrogen purification by applying PSA technology. And in the figure on the right, you see indeed what are the main input expected, so in terms of natural gas, water, and heat, and output expected from the system, so hydrogen and power, and also what are, let's say, the main building blocks the system should consist on. Next slide, please. So, as alluded before, one of the main goals is the flexibility in terms of production. So, in particular, already from the call, there was a demand for modulation and between nominal power production and a combined hydrogen and power production. And the CH2P system is designed indeed to work in 5 different operating modes that has been defined based on specific requests at hydrogen refilling station level. And so overall, we are able to cover a quite wide range, because we can go from, let's say, the nominal power and hydrogen production capability combined together, going down to 33% of the nominal electrical output and 15% of the nominal hydrogen output. In the figure on the right, you can see the operative map foreseen, and including, so the different operating model has been identified, and the estimated efficiency value that has been calculated based on system model. And for almost all of the modes that have been investigated, we expect an efficiency higher than 65%. And actually, if the efficiency, including the so-called three generation modes, so electricity, power, but also the useful heat is considered, then we could go up to 79% at full power and hydrogen production capability. But where we are now, so next slide, please. So, well, the core topic demanded for a prototype in the size of at least 20 kilograms per day of hydrogen, but CS2P aims to realize a system that is overall able to produce at full load 40 kilograms per day of hydrogen and 50 kilowatts of power. And at the present, we have a 20 kilogram per day module that is in assembly, and it will be tested in January 2022. And we have a second module also on the way, an improved module actually that is now under construction. So the final step would be to integrate this two module to get them what we consider as the final CS2P system sites, and they will be integrated into 240-feet container and tested at Shell premises in Amsterdam. And thanks to this second improved module, we will be actually able to operate just the system also in electrolysis mode. So next slide, please. Well, regarding the main challenge that we have been facing, they are mainly related to the development of such innovative single component and also their integration into a large and quite complex system. For instance, the flexibility in terms of production had a consequence on the design of each component. And this was requiring most of the time a really high degree of customization. That also means that time is needed for the test and the validation of the performance of each component. So let's say already starting from the design up to the validation, it was a long path and sometimes difficult because of course we were affected also as other EU project by the pandemic issue. And another crucial point for the CS2P system is the high level of integration that, of course, is needed when then both the efficiency target and, let's say, a very flexible operation are pursued. So this was resulting overall in a high degree of complexity on multiple levels. So from the design to the manufacturing to the assembling and even, let's say, the overall control of such system. The consortium, we are, let's say, still dealing with this with a continuous commitment. So definitely, I would say one of the lesson learned is that the development of such technology at this innovation level is time demanding. But after all, we were able to test each single main component, and they were showing performance in line with the design target, and in some cases even above them. For instance, for the LSM module. So now we are really looking forward to test the prototype and see what are the results, and also how we can then exploit the knowledge gained in CS2P. And on this regards, next slide, please. Yeah, so here you can see what are the key exploitable results that we have identified. First of all is the CS2P prototype itself that could be directly used by Agir as a system integrator in the CS2P follow-up project Switch. You may have already heard about it from previous section. So what we intend to do in Switch is to upgrade the CS2P prototype in order then to be able to operate it in both in fuel cell but also in an electrolysis mode. But then beside this, the prototype itself, we have identified also other two exploitable results. One is the flexible PSA that has been designed by Agir, that was needed due to the different composition and flow rate that needs to be the process to be able to recover the hydrogen at the needed purity level, and that could be directly commercialized by Agir. And of course, also the large stack module developed by Solid Power that can be also, let's say, the entity interested for this directly commercialization. And finally, next slide, please. So how we expect to impact on the transition to hydrogen mobility? Well, as I stressed before, once again, be a system that can produce flexible and reliable hydrogen and power. We were targeting lifetimes of this system of the, let's say, overall system of 10 years and lower, a little bit lower than what respect the LSM itself. And our targeted customer are basically oil and gas company, as indeed one of our partners, Shell, that can be indeed interested to innovative technology to address the market of hydrogen and electric mobility. And so potential end user then could be a driver of fuel cell vehicles or battery electric vehicles. And I want to add that another let's say relevant aspect is related to what is a little bit the hydrogen model cost of CS2P, where actually we can take advantage of the higher cost of the electricity from the grid, because we as able to produce also power, then this can reduce then the overall cost of the hydrogen production. And with this concludes my presentation. So I would like to thank you for the attention and to have the possibility to present such nice project and all the CS2P partner for the dedicated effort. Many thanks.
Thank you so much, Ilaria. And indeed, I mean, you've mentioned the flexibility, that solid oxide cells technology can offer, which in a system where we will have more and more variable renewables, I think certainly have a great potential to play a role in there. I have received a few questions, and I will take maybe the most initial one, if you want. And they were asking about solid oxide technology in general, if you want, and it's about how can you heat up, or what energy is used to heat up solid oxide fuel cells at such high temperatures of 700-800 degrees. And does it only happen at the beginning, or is it energy needed to keep the high temperature? I don't know if that's something you could answer.
Yeah, well, the system, it has been designed, in a way that, to perform the heating up, we can just use heat generated in a burner, but we were so let's say we use the large flow of air sent to the cathodic side to heating up the stack. And it's true that can take few hours, so it's long times, but once it's on temperature, then yeah, we can keep it hot. And indeed, I have not mentioned that actually the overall mode, operating mode that we have are in total 6, because we have an additional one. There is the hot standby mode, where we indeed keep the system hot by providing heat via the hot flue gas produced by burning natural gas. But with a, let's say, well integrated system from thermal point of view, the overall natural gas input needed to keep the system hot can be optimized and reduced.
Okay, thank you so much, Ilaria. And now a question in relation to the applicability. I mean, you've mentioned, or I've heard that the most immediate application, if you want, is for hydrogen refueling stations. So you are looking in the project at a 50 kilowatt system. And there are 2 questions in relation to that. One, is this the size of the system that you would consider for a representative installations once you have it installed in a real location? And the second one is, what is the highest quality of the hydrogen that you have achieved? Bearing in mind, this is going to be for mobility, where high purity of hydrogen is needed. What can you comment on the quality of the hydrogen as well? So on 2 things, on the size of the final system, and then on the hydrogen quality.
Yeah. Okay. Well, for what concerns the quality of the hydrogen, I have to say that we still have to test the complete integrated system, but we were able to test the single components, so also the PSA, and we saw that the purity target needed was achievable. So basically, the key component of key contaminant are, the CO and also nitrogen partially, and so we were able, let's say, to indeed get what are the targets. So if I will recall, is 200 ppb of CO and 5 ppm of water, and up to 300 of nitrogen, ppm of nitrogen. But then, of course, that will be then confirmed when we will test the complete system. So by having all the module integrated together. And then for what concern the site, well, of course, let's say we start from actually an overall hydrogen and power production that was much bigger. So let's say up to 1 tons per day. So this means that with such type of system, we have to consider that several modules needs to be then integrated together, to then be able to get to reach such final output. So I would say we for example, even within which we were indeed targeting this 1 tons per day of hydrogen production.
Okay. So it's a modular approach, basically, not that you would be. Okay, I see.
Correct.
And now one last question that is also coming from different angles, so trying to put it all together. It has to do, if you want, a bit with the business models, and I think there is a fair question here in relation to how the recent increases in the natural gas prices could affect this type of systems, because of course you are generating hydrogen, not only, also power and waste heat that could be used, but eventually at the current stage it's running on natural gas. So how that could affect and how could the versatility of the system take care of that? And then related to that, I will add, in terms of the targets for hydrogen production that you mentioned, 4.5 euros per kilogram, how far or how confident you are that you will get there? I know the project is still ongoing, so maybe it's not a fair question at this stage, but if you could give some hints of how things are going in this direction. Thank you.
Yeah. Well, for what's concerning the fact that we indeed use natural gas, I want to say that the system is in principle designed also to process also biomethane. So let's say considering a sort of flexibility in terms of fuel that's could say partially cover this issue related on cost of increasing cost of natural gas. But as I said before, also the fact that we with the possibility from such system to co-generate hydrogen and power, maybe this also gives some gain on margin, and to let's say to balance the cost of the natural gas feedstock. And then for what concern the hydrogen cost, yes, indeed, we are still, let's say, need to get result on it, and definitely, this 4.5 euros per kilogram, it was quite challenging value. I will say that maybe in the range of 5-6 something that could be maybe achievable.
Okay, thank you. And you brought a very good point, because it's true, it can run on biogas, biomethane, so you could even see on that versatility an advantage. And then you introduced very briefly already the switch project, where maybe can also use the electricity probably in these moments where the natural gas price is expensive. So indeed, I mean, this flexibility there. Thank you, Ilaria. I mean, exciting projects, and really looking forward to see now and to move to the full size system tests. So looking forward to these results. Thanks so much for.
Thank you.
Thank you. So we now move to the very last of our presentation before the coffee break. And I'm very happy to pass the floor to our last speaker, Professor Massimo Santarelli. He's a professor in the Politecnico di Torino. And he's the project coordinator of the remote project, and he is going to present today the progress to date. Massimo, the floor is yours. Thank you so much.
Yeah, thank you, Antonio. And so good morning to all the audience, and I'm happy to see a lot of good friends working on this important topic. And so the project I'm going to present, I'm the coordinator, the scientific coordinator of the project, but you will see is a big consortium. The name is remote, is related to the remote, already explained the topic, is related to the application of a system of storage. So basically power-to-power system based on the suitable, good integration of closed batteries and open system like hydrogen system, so electrolysis and fuel cell, to totally cover remote location only using the local renewable. So local load are totally covered for every hour of the year, so winter and summer, day and night, using the local renewable only thanks to the effect of using a hydrogen system as a storage technology. So the project, in this case, we will see a technology which are at the level of temperature, which is the low temperature as a difference compared to the previous discussion. So the project started in 2017 and will end in 2023. So we started in 2018, sorry, the call was 2017. And we arrived to 2023. We had an extension for a reason that I will explain. And the achievement at the moment is around 70%, we will see. And the total budget is 6.7 million euro with a funding from the European Commission of 5 million euro. So next slide, please. So here we can see the consortium. This guy is quite big and a very good consortium, I can say, very collaborative. So starting from the right, I can say the Greece, we have CERT and Horizon. Horizon is the end user of one of the demonstrator sites, and the CERT generate the analysis of the data. Then we have Politecnico di Torino, which is the coordinator of the project, and make an analysis of most of the data of the demonstrator. There is ENGIE EPS, one of the supplier of the technology, still in Italy. Then we go to Norway. In Norway, we have one end user, which is Tronder Energy, one of the end user in the site. and SINTEF, a very well-known research center that make also the analysis of the local data. And then we go to Denmark, where we have Ballard Europe supplying, which is a manufacturer supplying fuel cell to one of the, we will see probably two of the demonstrators. Then we go to France, where there is, to Belgium, where there is Hydrogenics Cummins supplying the electrolyzer section. And then we go to France. Powiden is a system integrator of one of the demonstrators. And finally, to Spain, where we have Inicom, which is a system integrator again, and the two end user, Capisa and ITC, end user of the local demonstrator. So you see, they are a big consortium, but very collaborative. Next slide, please. So the idea is, as I already said, to totally cover local loads. We will see basically farm industries in all the three cases using the local renewable. So will be renewable in the depending on the local weather conditions. So mostly wind in the north. We will see in Norway, photovoltaic in the south of Europe, and also hydroelectricity. So using the local renewable, local availability, the local load are totally covered for all the hour of the year, and making use of a suitable integration of closed batteries and hydrogen system. We have demonstrated also with many calculations that this is the best way. So the integration, I mean, to cover this type of cost, or this type of load, minimizing the cost at the end, also the size of the components. So we can go the next slide. So why, of course, to cover with this type of system the local load using renewable? The reason is that in remote application is very clear. So we have in this remote application usually we are using the genset. So that using diesel, the genset using diesel, of course, produce local pollution, which in many cases, especially in remote community, are not. I mean, a good point, and also at the global level at the end are not a good option. But also I can add in this type of location, also the cost of this way to supply energy becomes very high. So we are not in the center of a city, of a big city. I mean, we are in remote location to supply the diesel fuel in this type of location become very costly. So already now this type of site can be a very interesting user case. Even now with the current cost of the technologies, so they represent a business case of interest in the short term. Why this? Because as I said, reduction of local pollution, increase of the energy autonomy of this type of system, so without relying to external supply. The better stability also of the microgrid, which are connected to this type of loads, and as I said, can be also a good economic case. All this only with battery at this size is totally not economically interesting. I mean, it's too expensive, and also the size will be very big. But the integration with hydrogen becomes a very good business case, especially when considered we have to cover the level of the seasonal level, so not only day and night, but of course a level of the season. Okay, so next slide. Here we can see the first demonstrator. So the first demonstrator is in Rie, which is close to Trondheim. The load is agri-food industry, and the local renewables that we use are basically wind, a suitable combination of wind and photovoltaics. This combination works very well. They complement each other. We see that we see in the picture the site that is running since close to 1 year, and the size is at the level of 50 kilowatt of PEM electrolyzer. To give you an idea of the system, 50 kilowatt of PEM electrolyzer, 100 kilowatt of PEM fuel cell. All these complemented with a storage. You see in the picture on the right side, a storage of compressed gas at 30 bar of hydrogen at 37 cubic meter, and a battery module of 550 kilowatt hour, which is quite important, but we will see it works very well in complementary with the hydrogen section. This site is already started in December of last year, in 2020. So now it's running very well. We will see some result, and the target is to go on possibly for the next year. We will see. We are in discussion about this. So the achievement is around 50%, we can say. So next slide, please. The next demonstrator that is already running is similar in terms of load. It is again an agri-food industry, but it happens frequently in remote location, apparently. And in this case, the site is in Greece, in the border with Bulgaria, so in the countryside. And the situation is totally different, because in this case, the renewable is more controllable, because it is an hydroelectric plant. So, of course, compared to a wind generator and photovoltaic, the controllability is higher. In this case, is mostly used the system to generate a backup and safety in order to guarantee the continuity of the operation of the agri-food, because the type of renewable is, as I said, more controllable. Because of this, the size of the storage is smaller. So we have in this case a 25 kilowatt of alkaline electrolyzer, so you see the size is lower, and 50 kilowatt of PEM fuel cell. Also, the battery is smaller, is around 92 kilowatt hour, and the storage in hydrogen is 12 cubic meters. So you see, of course, depending case by case, the size can change, especially depending on the type of renewable. With more controllable renewable, like in this case, hydroelectricity, the size can be lower. Anyway, the system is in operation since more than 1 year. You can see the picture of the installation, where we have the module of the electrolyzer, the fuel cell, and the control module. And the system is running since, as I said, October of last year. It still is in operation also next year. So we can go to the next slide. The last one the last one is still in progress in terms of construction because of some delay that have been achieved occurred during the project. So it's let's say a new site compared to the original proposal, and this new site is in Spain, in the Canary Island, so in an island, which is a classical site of remote type of application. In this case, as I said, we are still in the construction, so the system will start in operation in July of 2022. The scheduling of this new site is going very well, but as I said, the delay was before. And the load is again agri-food. In this case, again, the renewable are photovoltaic and wind. And the system is of the size similar of the one that we have in Norway. So 100 kilowatt of PEM fuel cell and 85 kilowatt of alkaline electrolyzer. So the electrolyzer is a little bigger here. Again, complemented by a storage of hydrogen of 50 kilogram at 200 bar and 200 kilowatt hour of a battery. So you see in every structure there is a battery complementing the hydrogen system. So next, please. Some result in terms of KPI. I just reported here, not to be too long, the KPI in terms of round trip efficiency in the site of Norway. The site of Norway, if we want, is also, I can say, the more complicated because of the weather condition. But anyway, as you see, the KPI in terms of round trip efficiency are quite interesting. Of course, when the battery has a higher role, the round trip efficiency is higher, like in some central morph, you see, say 72%. Of course, this means that the battery has a role which is not negligible. And then go around the value of, you see, 58, 53, when the role of the hydrogen system becomes bigger. But anyway, the role of the hydrogen system is totally necessary in this type of system of this size and in this type of weather condition. So this round trip efficiency is totally acceptable from my point of view. So next one, I would like to show you the behavior of the system. Is very interesting. In still the system in Norway. So in a day of February, day and night. So you see during the night, there is no sun. There is a small amount of wind. And you see at the beginning of the night, there is the discharge of the battery. So you will see the red line going down. When the control system see that the state of charge, which is a parameter very important, arrive below 30%, the fuel cell start. So if a cell start, go in operation, in this moment, in this case, go in operation to 40 kilowatt, depends on the night request of the load. And then the wind in the simultaneous recharge the battery. When the battery is recharged at 30%, the battery go in operation to increase the round trip efficiency. So go in operation and is discharged. So you see that the fuel cell go down to 20 kilowatt. So there is a very good integration of the fuel cell and the battery in real time, let's say. So this is during the night. Going in the day, so on the right, you see that the sun started to rise. So there is a good photovoltaic effect. The photovoltaic cover the load and recharge the battery. So you see the fuel cell can go down in operation. Then when you arrive in the late afternoon, no sun, battery not so much. So fuel cell go to 40 kilowatt. You see the dynamic is very, very, very good in my point of view. So you see an example of a not easy day because it was in February. So next one. Some KPI similar for the demo in Archkistro in Greece. Again, I have reported the efficiency of the average efficiency in the month of the electrolyzer of the fuel cell. And again, you see that the KPI in terms of round trip efficiency can be very high in some moments because of a role of the battery, which is important. So we are higher than 80%. Of course, the battery here is very operating. In some other moment, in some other month, there is a bigger role of the fields of the hydrogen system, so the KPI are a little lower. But you see, in average, the KPI of the round trip efficiency during the year, in my view, are interesting, good level. So next, please. And the risk in the sense, challenge are several. Challenge has been, for example, the possibility to install, to have the permission for installing a renewable in some particular location. Like, for example, we started to consider the operation in Norway, in an island, which is called Frøya Island, but it was impossible to obtain in this type of island the permission to install a big photovoltaic, wind turbine plant. So we went to a onshore situation, so in the mainland, where we have now the demonstrator. So this has been one of the problems. The second problem during the COVID, the Corona, the construction has been, slowed down. So fortunately, we use some technology application like some glasses for special glasses for the remote control. So this were used by the people from Thunder Energy connected to the control in Paris of the system integrator. This has been a very good help. And finally, the big challenge has been that at a given moment of the project, one of the suppliers of the technology decided to reduce the intervention in the project. So we have been obliged to change one of the sites of the installation. So that's why we are now installed in Canary Island with a delay. So we can go on. And the exploitation and expected impact. The exploitation is already started. I can say that the manufacturer, from one side, are collecting a lot of technical data for the type of product. So we are getting, they can say better than me, a very good experience on this side. From the other side, the experience of the end user is very big. They are considering, especially to use a new possibility like machine learning, like weather forecast to better make the control of this type of system in the future. So there are a lot of interesting outcomes that can come from this first type of experience. Also for us, after the start of this activity, we have started several other activities in terms of installation. For example, we are making a big project in the Sardinia Island in Italy of a power-to-power system that bigger size compared to the one in remote. So we have get an experience that now we can use in other type of installation, and we have a lot of requests about from this point of view. In terms of impact, the impact is locally interesting, so lower cost and no emission basically. But if you go up to this, if you go at the global scale, we see that at the end, making an analysis, more than 750 million people works in Ireland, only in Ireland. I'm not talking of all the remote situation. If we go to cover this type of sort of niche application with this type of system, we can save, we did a calculation, around 4% of the global emission of the CO2. So I think this type of adoption in a remote area seems niche, but are not at all niche. They can be really a good early adopter, also because, as I said, the cost of the energy in this type of location is not the same cost that we have in a municipality in I don't know, in the center of Germany. Okay, next one. And going to the end, I go rapidly. We have done a good, I hope, good communication activity. We started with infographic, but now we have video. Next one. We have also is a good. Thank you. So we have a good achievement in terms of award. We have won more than 4 awards for this type of project, and especially the first award, the first in the score in the European Sustainable Energy Week of 2020. So we have been awarded in terms of best project. There has been a good satisfaction from the project, and we have several type of communication in the press and in the media. And going to the end, we have produced. So we have video, of course, but we cannot show now in this presentation, where you can see in the website. And then the last one, we have produced also some scientific paper. So maybe the next one. But anyway, we have we have produced some scientific paper, and of course we have been invited in several international conferences in Europe and abroad to present the result of the project. So I think is all, and thank you for listening to my presentation.
Thank you. Thank you to you, Professor, and for the details provided on the data. It's always very nice to see this detailed analysis and the results you are getting from the demo. Unfortunately, I also take note of the time, so we extended a bit, and we are now on the team 15 time. So I have only time for one question and one quick answer, and it's here in the chat, and it relates to the complexity of the projects, which likely may be associated also with some delays. So what could be your lesson learned, if you had to summarize it in one phrase, about how to go into the next time that you do implement such a project to make them smoother, maybe about permits and things like this. So if you can provide a quick answer on that.
Yeah, the permit has been one of the cause of delay. So I can say, not particularly the COVID, because with the technology that we have now, it's possible also to operate in remote, as we know, as we are doing now. But especially the permits has been an issue, because especially in a remote in a site like this one, there are a lot of protection situations that we have to consider. Of course, they are important, but in some way we have tried to save the local condition and to save also, I mean, the climate in the same time. So if we consider systems that are totally fed by renewable, and this can be done now thanks to this new technology that we have, the technology that we are developing in the last 20 years. So basically, battery from one side, the hydrogen system from the other side. I think this is a way to protect the environment, to protect, I mean, the local communities, to reduce the cost of energy. So in some way, I think that this type of system could be considered as in some way something that has to be also as a protection of the local environment, and not something that is invading and creating problem. But yeah, I can say in this type of system, the permission is very important to start very, very early, because otherwise you find problem. Yeah.
Thank you. Thank you very much. And there are some other questions in relation to the maintenance, being these remote locations, and also about potential replicabilities. But I know that you do have a very good network of social media and availability to reach. So I would suggest that anyone could get in touch, of course, with you and your team if they wanted to know more. So
definitely. So yeah, of course we are very interested to communicate. I mean, the project, I think the result is very good. I can give you all the details.
Thank you. Thank you very much, Massimo, again. And thank you to all of you. We come to the end of the panel. So I really wanted to thank you very much for the presentations, for your time in preparing that, and also for taking all the questions that we have had. And yeah, I wish you all the best with the finalization of your project. So I'm sure we will see you soon. So thank you. And to the audience, I want to tell you, just grab your coffee, because at 11 o'clock, we will have a follow-up session, looking this time at the research activities that we have on the field of fuel cells for a stationary application. So thank you for your attention. Thanks to the speakers. Thanks for the questions to the audience. And I wish you all the best to everyone. Thank you.
Thank you.
Good morning, everyone, and welcome to the parallel session on fuel cell technology for stationary applications. We will have a number of projects presented now on the results of our research projects for applications of fuel cells for heat and power. We have a mix of projects looking at the next generation of cells, looking at proof of concepts, looking also at manufacturing. So I'm very happy about that and to have the chance to listen from all the speakers. So these sessions will bring us to 12:20. Now I'm going to pass the floor to the first speaker to present the results of the ongoing progress of the project NewSOC. And the speaker is Anne Hagen from the Department of Energy Conversion and Storage Electrochemistry in the DTU, Danish Technical University. So Anne, the floor is yours. Thank you so much.
Thank you very much. Ladies and gentlemen, it is my great pleasure to present you today highlights of our project, Next Generation Solid Oxide Fuel Cell and Electrolysis Technology, NewSOC. My name is Anke Hagen and I'm from Technical University of Denmark. Next slide, please. Yes. The project was a response to the call in 2019, and we started the project the 1st of January 2020 with a duration period original of 3 years. We started out with a kickoff meeting in January with a great enthusiasm, a big participation in Denmark, and then 2 months later we were hit by the COVID-19, which meant that all our labs were more or less closed for several weeks, and we also had some restricted access to them for quite a long period. We asked for extension and got granted a project extension, and therefore it will run for 3.5 years. That means we are circa in the middle of the project. The budget is 5 million euro, and we are quite a large consortium comprising of 16 partners, 11 research institutions, and 5 industry players. In fact, these are the 5 major European industry players in the solid oxide fuel cell and electrolysis area. You can see the logos on the right-hand side and down below the distribution over 12 countries in Europe. Next slide, please. We have in the past days heard about the urgency to roll out hydrogen technologies. And we believe that solid oxide technologies, both fuel cell and electrolysis, can play a major role because they are capable of integration, they are versatile, they are flexible, and they can combine sectors, integrate them, power, gas, and heat, and thereby can be key enabling technologies for both the green transition, but also for green future energy systems. Next, please. The NewSOC project aims at improving state-of-the-art fuel and electrolysis technology in regard to performance, durability, and cost competitiveness. We have already seen that solid oxide technologies are commercial, are in demonstration and field testing, are about to roll out and scale up. And the NewSOC project provides significant support for this establishment by developing already existing materials, improving them, and also by providing next generation concepts and materials to be successful on the long run. Next, please. We have defined 5 targets in the project, our 25% targets, that include an increase of the electrolysis current at low degradation rates, a reduction of the area-specific resistance, an increase of the cyclability. And here we know that these technologies are flexible. We can run both the fuel cell and we can also run the electrolysis in a dynamic mode, following fluctuating energy input, and we can also run in a reversible mode. We want to improve the durability in those operating modes. We also target a reduction of the manufacturing costs and the reduction of the use of toxic materials in the manufacturing. How do we want to achieve these targets? Next, please. We have activities in 3 main areas. Next, please. And these are developing the structure, innovative architectures, developing alternative new materials, and third, innovative manufacturing. So by having our activities in these 3 areas, we try to reach the promised targets. More specifically, next slide, please. We are proposing 12 innovative concepts. Next one, please. And as you see in this illustration, these concepts tackle very different components in the cell and in the stack. They are addressing issues in electrode layers, in the depositing of layers, in interconnects. And if we go to the next step, we can see, so next please, yeah, we can see them all listed. So 12 concepts where the research partners are focusing to improve state of the art. It is of course very difficult to select only a few examples for this presentation. However, I selected 3 examples which are in the areas of structural optimization, new materials, and manufacturing. Next slide, please. My first example is about the structural optimization, more precisely of the fuel electrode, an activity that is carried out by CEA from France. The state-of-the-art fuel electrodes contain nickel YZ, and we know that the performance and durability is strongly depending on the microstructure of these fuel cell materials, and also the composition, the ratio between nickel and YZ. We also know that in particular in electrolysis mode, a large part of the degradation is due to nickel depletion, nickel agglomeration, and loss of percolation of nickel. And the aim was now to both increase performance and also to enhance the durability. We know that this nickel depletion is actually caused by a large overpotential on this electrode. By improving the electrode, we would be able to reduce this overpotential and hopefully also reduce the degradation issue coming from the nickel movement, depletion, agglomeration, etc. CEA has carried out quite a large mapping of testing to map out the function of degradation rate versus operating conditions. They have undertaken microstructural detailed analysis to be able to establish a model, which you see illustration here of the microstructure. And they have a third step or third column developed an electrochemical model involving all the elementary steps. And now the target was to use this model combining microstructure and electrochemical performance in order to minimize the overpotential on this electrode by an optimum microstructure. The outcome of this target microstructure was guiding the manufacturer, and CEA succeeded to manufacture a cell with this improved structured fuel electrode, where they could increase the performance. As you see in the horizontal line, we went from a state-of-the-art current density in electrolysis from minus 0.75 amps per square centimeter to -1, which actually corresponds to the 25% target. Moreover, it was also observed that the nickel depletion was reduced or even avoided. That means we can operate at these high current densities, even with low degradation rates. Next slide, please. The next example is about the development of new electrode materials, more specifically cobalt-free oxygen electrodes done by TNO in the Netherlands. Cobalt has been identified as a critical raw material, and it is strongly encouraged to reduce or even avoid this in electrodes or in the cells. We know that the best performing state-of-the-art oxygen electrodes are composed of lanthanum, strontium, ferrite, cobaltite, or single cobaltite. And TNO has now prepared a number of different compositions of cobalt-free ferrite electrodes and mapped out the electrochemical performance. When you use these lanthanum, strontium, calcium, ferrite, then you can observe even at the best electrochemical performance, it is still worse as compared to state-of-the-art. And therefore, TNO used a structural feature. They have made a patterned interface between the electrode and the barrier layer in order to enhance the triple phase boundary and thus the performance. And on the horizontal line, you can see that indeed the performance in terms of higher electrolysis current, now minus 1.1 amps per square centimeter at 750 degrees centigrade, was reached. Next slide, please. And my third example is related to the manufacturing. Here, room temperature sputtering of the cathode barrier layer done by University of Salerno. This barrier layer between the oxygen electrode and the electrolyte has the function to avoid chemical reaction between these two phases. and the density and the grain structures determine to a large extent the performance of the cell. The room temperature spattering has a very big advantage of being able to deposit thin, even distributed layers, and the subsequent thermal treatment is able to establish the right grain structures to enable a high conductivity or low area specific resistance. And on the right hand side, you can see that cells that had these barrier layers were always performing better than state of the art by a more flatter IV curve. And on the horizontal bar, you can also see that we can reach -1 amps per square centimeter as an improved electrolysis current with cells that contain these barrier layers. Next slide, please. Also, in the other concepts we have working with, we have reached significant progress in the first part of the project in terms of performance, durability, and costs. And on the horizontal bar, you can see that we are in the range of having achieved 50 to 75% of the original project targets. Next slide, please. Of course, we need to implement all these improvements, and that is part of the project. And one more slide. We have in the project different cell configurations, fuel electrode supported, electrolyte supported, and metal supported. And all these are represented by the major industrial players working with these concepts. And we have mapped out the development concepts versus the industrial players and have now identified where and in which cell or single stack or short stack we would like to integrate the improved elements from the project. And that is actually a step that is currently in progress. And then the next slide, my final slide. Of course, we need to spread out and share the knowledge that was gathered in this project. We have a homepage, we have the social media, and we have a big share of student education, as you can see, in terms of PhD, master students, and postdocs that have been involved in the project so far. And we contribute as well to the scientific knowledge by journal contributions, by conference contributions, and organizing workshops. And we hope we will even improve and speed up with this outreach and communication in the forthcoming project period. With this, I would like to finish and thank you for your attention.
Thank you so much, Anke. Thanks a lot for sharing all this with us. I mean, your presentation has provided a big number of areas where you are working at, and certainly very good progress in a number of them. But my question is coming now from the angle of managing such a project. I mean, I understood that you have 16 partners, and it's very interesting because you are really bringing all the research community or most of the research community on the field of solid oxide cells, also the main European industry actors in there. So how is this being handled? I'm thinking, for instance, when it becomes to issues that could arise like intellectual property, but also in terms of how everyone could benefit not from the findings, and how do you see that the project will end up at the end benefiting actually our industry? How is that going to be managed? I don't know if this is something you could cover. Thank you.
Yeah, thank you very much. Indeed, it is a very large project and maybe even containing competing industry partners. At this stage, and of course, we managed how we want to treat the IPR that we managed in the consortium agreement. And my experience so far is actually maybe a bit surprising. It is a very openness from the industrial side. We have managed to do some workshops where we actually addressed what are the targets that they are going for in the different industry. And as I mentioned, there are different cell concepts. For example, the fuel electrode supported, electrolyte supported. These are two concepts that are working at completely different overall operating conditions. And the industries like Sunfire, Solid Power, Elcogen, they have different targets they want to achieve, but they were quite open to share them. And this is maybe an expression that they know at this stage we need many forces to solve generic issues that can give benefit to all of them. This gives like a more benefit than being secret or confidential. So right now we have quite good experiences with the exchange, and we have very also an openness to integrate into cells. So in principle, all the partners are in close discussion with one or two industry partners, where they then at this stage and the forthcoming weeks would like to integrate layers into their cell or stack platforms. And we have already a few examples where there were electrodes like deposited on half cells from industry players. So I experienced a very good openness to share the more generic solutions and to try and integrate them.
Okay, thank you. It's very good actually indeed to see this collaboration between the research community and industry indeed. Other question that is coming also through the audience more on the technical side, it's about the durability targets that the project is targeting. You've mentioned at the beginning of your presentation, and I mean, progress has been done already in solid oxide fuel cells, which if you want are one step ahead on when we compare with solid oxide electrolyzers, in the sense that they were maturing and research started earlier. But so what is the challenge here? Is getting larger durabilities for solid oxide fuel cells? Is the challenge keeping the current ones when we are operating the cells in reversible mode? And which targets could you get at the end of the project? So could you comment a bit on that?
Yes, thank you. Yeah, the durability is one of the critical issues or challenges, you might say. We are in electrolysis mode. We are targeting below 1% per 1,000 hours. And the final step, we also want to carry out quite a long-term test to validate this, 5,000 hours. And I think even with the mature versions, we can achieve low degradation rates. However, what is the main operating parameters that comes into play is the current density. And the current density is like a direct measure of how much hydrogen we can produce in electrolysis mode. That means we can, of course, operate quite stable at, let's say, medium hydrogen production rates, but at the end, we would like to enhance the hydrogen production and go to higher current densities. And that's why we are trying to develop more durable electrodes that can withstand these higher current densities. Talking about reversible mode, there are maybe a bit contradicting experiences. So far, actually, we have not seen additional degradation mechanisms or additional degradation when we are running in a reversible as compared to one of the modes like fuel cell or electrolysis. So we don't see any additional effects. And the same applies when we are running in a dynamic mode. That means we are running dynamic solid oxide cell. It would be a dynamic current load, or vice versa. And the electrolysis following a wind profile, for example, as electricity input, we don't see additional degradation in the dynamic modes. So I believe when we are able to increase durability at the constant mode, it will also be a step forward to be able to run in diverse dynamic regimes.
Thank you so much. And last question that we have also from the audience. They are talking about the efficiency and the lifetime. I guess lifetime, not clear to me whether this to be understood for durability as you are working on cell and short stack level, but on the efficiencies, are you looking at that? Is there still work to be done at the efficiency side?
We are not so much focusing on efficiency, but on the degradation and performance and the other targets that I mentioned on costs for manufacturing, avoiding toxic materials. And in a way, we are building on the generic, well-known high efficiencies we can reach on the system level. However, in the frame of this NuSoc project, providing next generation materials and cells and elements for short stacks, we are not so much focusing on increasing system efficiency. Here we actually rely what is already achieved, which is, as we heard also in this week, which are quite high values, like over 80%, 85% in electrolysis systems. And we also know that in fuel cell systems, we can also achieve over 60% electrical efficiency already now. So this is not a specific target of this project.
Indeed, actually, when we were presenting the portfolio of activities, the Switch project, which is using a solid oxide fuel cells in reversible mode, they on the test at the large stack module, they were observing 97% hydrogen production efficiency in solid oxide electrolyzer mode, of course, using waste heat. But indeed, that confirms what you're saying, that it's about already keeping the good efficiency values that we are already getting in the projects as well, of course, and in the systems. Thank you so much, Ank. That will be for now. I want to thank you so much again for your presentation. And I'm very happy to give the floor to the next speaker, which will be talking about the Empower project, Mr. Johan Dahlgren, Senior Scientist for Fuel Cells and Hydrogen at VTT in Finland, Technical Research Center of Finland. So Johan, the floor is yours. Looking forward to hear your presentation.
Thank you, Antonio, for the kind introduction. And ladies and gentlemen, I will be giving a short overview of the Empower project, European methanol-powered fuel cell CHP. This is a three-year-long project. We have a EU contribution of 1.5 million euros, and this started in the January last year. We are now in the end of the second year of the project, and we will be finishing it in the end of next year. This was a response to the call year of 2019. Next slide, please. A short summary of the project. So we are targeting to develop, manufacture, and validate a 5 kilowatt methanol powered mini CHP system. We are basing it on the high temperature PEM fuel cell technology. Targets here are to achieve a high system efficiency, about 50%, and to improve the stack design, and to increase the fuel utilization about 95%, and improving the stack efficiency about 55%. We will, in the end of the project, demonstrate this system, the CHP system, with a validation run about over 2,000 hours. This will be done at an end user location in Finland, and we are also looking to have a part of this to fall during the winter months, so that we will demonstrate it in both warm and cold environments. That's why we have the picture here shows a mobile workspace. This is a trailer mounted mobile workspace which can be transported to the location of the need of the heat and power. This provides shelter both to the operator and to the system. And apart from this 5 kilowatt system, we are planning a scale up for the system for 50 to 100 kilowatts, and also a business analysis to see the whole methanol fuel cell value chain. Next slide, please. This CHP system is aimed to replace diesel generators, both for power and heat production, as backup power and heat for mobile network systems, single houses, renewable energy systems. We have also identified field hospitals, raw water test pumping, construction sites as potential end users. And the system targets, as I said, we are aiming for high electrical efficiency. It should be also compact. The volume should be less than 160 liters. That is not including the mobile workspace that I showed you here in the last slide, but only the system. We are aiming for a quick startup time for less than 10 minutes and a cost less than 3,000 euros a kilowatt. This is significantly lower than the multi-annual work plan targets. Next slide, please. We have 5 partners in this project. It's coordinated by VTT from Finland, and THD Control, also from Finland, is the system integrator, who will also demonstrate it in the middle of Finland. Katator from Sweden is producing the fuel reformer system, and Blue World Technologies from Denmark is developing and manufacturing the fuel cell stack and the fuel cell system. We have the University of Porto joining from Portugal, who is working on reformate catalysts and MEAs for the stack. Next slide, please. A short overview here of the project progress. We have moved from the system specifications and planning to a construction phase, and the reformer systems and fuel cell systems are currently being set or manufactured and integrated at Blue World's Blue World's site and will be shipped to Finland for final integration next year. Looking on selected KPIs and where we stand in terms of these, the system costs, which should be lower than 3,000 euros, have been seen to be achievable with a production of 20,000 units a year. The target in the multi-annual work plan for 2024 is 5,500 euros a kilowatt. So I think we are quite well in ahead of this target, which is really nice. The startup time, which should be below 10 minutes, hasn't yet been tested as we don't have the system ready yet, but according to dynamic simulations, we see that this should be possible. The fuel cell stack efficiency should go above 55%. This has been demonstrated already with single cells with pressurizing the stack. We can also already show efficiencies above this. So we are confident that we can reach the fuel cell stack efficiency as targeted. The system efficiency above 50%. This will be validated in the demonstration phase, and we are working to improve the system and decrease all parasitic losses and so on, that all that is affecting the system efficiency. So this is an ongoing task still. And we have also a KPI on the fuel processor efficiency, about 85%. This is achieved at the moment, and the fuel processor is being set up together with the fuel cell stack. Next slide, please. On the exploitation part, we are aiming to both bring a new product to the market to end users who have already been identified. THD as the system integrator has already in the beginning of the project had extensive discussions with many potential end users, and we have formed our system and product also in the line of the wishes from end users, which we have tried to take into account already in the beginning of the project. So that's why we see that the product will fill an existing and identified need, and we are expecting that we can deliver such systems about 1 to 2 years after completing the project. The project also supports the industrial partners, both in developing the system and know-how, and also directly by supporting the factory ramp-up of Blue World Technologies, who are currently setting up a factory for the products in Denmark. And for the 50 to 100 kilowatt system, we will look into marine applications, where we see that the methanol would be an interesting fuel for the future. On the impact side, we do have the most important impacts would be the cost decrease, high efficiency, and also to strengthen the EU knowledge on the technology. We also work on creating synergies and joint ventures, and I think we have during this project we have achieved very well cooperation between the industrial partners, which has resulted, I think, in a good end product, and also improvements in the know-how of different partners. Next slide, please. We have on the communication activities, we have tried to be very open. We are having 4 open public events during the project. Unfortunately, we have been forced to have all these virtually still due to the pandemic. We have had we are promoting those and the project results on our website. Please check that out if you're interested. The social media presence, we have tried to work on through our own LinkedIn page, and also working on the visibility at the partners' social media channels, Twitter, LinkedIn, and so on, which do obviously have a lot of more followers already because they are established in the social media platforms. We also, of interest, might be we have a video here to promote methanol fuel cell applications. This can be seen on our project website. This is a really down to the basics. So this is targeted for the general public. Next slide, please. As our last activity, we have the dissemination activities. We have up to now one article published. We have 2 in the making. Within the project, we have had 2 master theses which are finished and 1 PhD thesis ongoing. And those events that I've mentioned earlier, we had a webinar on the methanol-powered fuel cells and the potential of renewable methanol. And this fall in September, we arranged at University of Porto a summer school on hydrogen economy. This was a virtual one, had close to 100 attendees all over Europe, which we found really encouraging. And also, of course, we are sharing our public deliverables. This was a short overview of the project. Please, if you have any questions, I'm happy to hear them.
Thank you. Thank you so much, Johan. Indeed, very nice to see the progress as well, and something different, high temperature methanol. We've seen actually the former session where we were presenting a number of demonstration projects. We've seen solid oxide fuel cells for remote applications, a small scale, also micro cogeneration with solid oxide fuel cells, and larger commercial systems, low temperature PEM for cogeneration, heat and power at homes. Now we have high temperature PEM with methanol. So could you tell us what is the propositions? I mean, why to go for high temperature PEM, why methanol, and what could you share with us on that?
Yes, methanol has the advantages that it's a liquid fuel, it's rather easily available. It's the logistics is more convenient than compressed hydrogen, for example. And on the high temperature PEM fuel cells, fast startup times, and do accept small amounts of carbon monoxide, which makes the system slightly smaller, slightly more compact, when the reformer system is can allow for up to 3% of carbon monoxide, and it's having we also have the high temperature heat coming out from the fuel cell. We are working at a temperature of around 160 degrees. So we are setting up the system to include heat pumps, and it has, at least here at the bit of northern parts of Europe, it has its own value.
Thank you. Thank you. And related to the methanol as feedstock, we just received a question. I don't know if you have that information or whether it's something you are planning to do, but if we compare it cost-wise with others, with using, for instance, LPG or ammonia to supply the fuel cells, what would be the comparison, or are you planning to do such an analysis, or what would be your opinion on that?
Yes, in the end of the project, we will have we will be looking into the carbon footprint of the system. This will also include the fuel supply, logistics, and fuel choices. So I think obviously it might be big differences on the scale or the size of the system. Here we are having a 5 kilowatt system that we're building, but we're also looking into larger, up to 100 kilowatt systems. So I think there we might find changes on also how it affects carbon footprint of the systems. But this is something that we will be looking into during our last and third year of the project, when we do have the more information on how the system itself will look like.
Okay. And looking at the end users, if you want, I mean, the project is putting together a proof of concept at 5 kilowatt electric rated power. You mentioned during your presentation that there are plans to scale up to 50 to 100 kilowatts, and that end users could be stationary applications, but also marine applications. But my question here, is the 5 kilowatt system also representative of a potential end use? And what do you see coming first after the project, if the project manages to reach its targets, to bring it to the next level in terms of readiness level? What would you see more suitable, stationary, maritime, and the type of sizes that you will be targeting? If you could share that with us.
When looking at the stationary part first, I think already the 5 kilowatt systems, they have been shown. There's been big interest from network companies and waterworks.
Hello, everyone, and welcome back again. There were some technical issues which have been resolved. So basically, we ended up the conversation with Johan, summarizing a bit the European supply chain on high temperature PEM, looking at all components. So I think with that, I would conclude that indeed there is good prospects for exploitation of the proof of concept being developed in the Empower project. So I'm looking forward, Johan, to see the completion of the project and to see the results and to see whether the KPIs can be achieved. So thanks again for your contribution and for answering all the questions. Thank you, Johan.
Thank you, Antonio.
So we move to the next presentation for Project Mamma Mia, and for this one, I'm very pleased to have Sylvain Bush from Johnson Matthey Fuel Cells. He's a fuel cell technology manager and test facility manager. So looking forward to hear the results of the project, Sylvain. The floor is yours.
Thank you, Antonio. So my name is Sylvain Bush. Within Mamma Mia, I am the technical coordinator, but also a big shout out to Jerry, who has been the main coordinator for Mamma Mia all the way through this program, and also Vladimir Bude, who started as the coordinator for Mamma Mia. So as you might have seen on the first slides, Mamma Mia, we won the Best Innovation Award last year. I think, Antonio, we should also be planning for another award on the most innovative project name. I think that would be nice. So a little bit about the project. So I know today in that set of presentation, we are looking at stationary fuel cells, but I think Mamma Mia should not be looked at within solely stationary application. This is a manufacturing project who applies for every single CCM manufacturing throughout the various different applications, and also has good applications towards electrolysis as well. So anything that has to do with coating, high-speed manufacturing, this project definitely applies. So as you can see, the project is now finished. Since June this year, we have now finished the project. I've actually presented Mamma Mia 2 years ago, and it does feel worlds away from the time when we could all be sharing this together. So I think I'd like you to quickly have a look at the partners, because this is quite an interesting project in that respect. So while we have our academic partners, we have the Fraunhofer ENES, we have Technical University Chemnist, and we have Unimore. It's the mix of capability and knowledge that is being brought forward here. So Unimore, the University of Modena, was bringing a lot of ink knowledge, particularly very strong knowledge in terms of inkjet printing. And then you have the Fraunhofer ENES and Technical University Chemnist, who were bringing a lot of pilot capabilities and also a lot of knowledge in terms of coating and printing. So they were bringing a very, very strong academic input into the project. And then we were bringing in the industrial partners. So they were a company called Systems. So Systems were very interesting, and this was also very much the aim of this topic initially, is to try to bring in other industrial partners which had not had any input into fuel cell industry previously. So Systems are a company that manufacture inkjet printed line. So the nice and the interesting part of this, they are inkjet printhead agnostics. Therefore, we could definitely work with multiple partners towards inkjet printing, which we'll touch upon later on. And there was ourselves, Johnson Matthey, which are one of the leading MEA manufacturer. We had NetStack as our stack partner. And then we had INEA, who are a integrator who do manufacturing lines. So a very, very good, very interesting mix of partners. Next slide, please. So what exactly were we aiming to do with Mamma Mia? So the aim of Mamma Mia is to move away from the little drawing that is on the left-hand side, is rather than having to coat on the multiple roles, so coating your anodes, your cathode, manufacturing your membrane all separately, or printing directly to your membrane. Every single one of those process steps are batch process. Every single one of those steps requires unwinding in order to be able to print the next coat. So the aim of Mamma Mia is to do additive manufacturing. So this is the little graph on the right-hand side. This means that we start with a backing, and we're going to start printing our first catalytic layer. Then we're going to start printing our membrane, adding our support, adding another layer of membrane on top of it, then our final catalytic layer, and finally add what we call the seal edge protection. So let's not confuse this with the gasket that goes onto the stack. It is the window around the catalyst coated membrane, which enables you to support the CCM. So this is really the aim of the process, is to have an all-in-one printed CCM, which can be manufactured at high speed. Next slide, please. Good. So I have the Mamma Mia KPIs. So in here, I think we've got to be very careful. First of all, those KPIs were being written for stationary. And if you look through some of the KPIs, some of the stack CapEx costs, they don't necessarily apply to Mamma Mia. We were not manufacturing stacks. We were really focusing on the manufacturing of the CCM itself. The power densities is the same. As most of us know, this feels really low, but the material set that was used within Mamma Mia is the material set that was used for Project Inspire, which had achieved 1.5 watt per centimeter square. So when I will show some of the power curves later on, I don't think we should focus on the actual performance, because how it was tested at lower current densities with flow field plates, which had much higher landing areas that you would have in an automotive stack. So what we were looking is performance and durability equivalence, not necessarily trying to meet a particular performance target. Where it becomes far more relevant is all the manufacturing KPIs themselves. So the metal loading, the material utilization, but the production wet speed was really important. Being able to bring really fast coating speed was key to the project. And finally, be able to achieve very high production capacity. Now, if we look at the targets that the EU has set of 100,000 trucks by 2030, this is several millions of MEAs that have to be produced. Concurrently, in terms of capacity, the capacity would not be there. So we have to find better solutions. Next slide, please. So when I last presented Mamma Mia in 2019, we had gone through a assessment of the different coating techniques, and we had demonstrated some of these techniques at 50 centimeter square scale. And we had been able to demonstrate the concept that we were able to actually reproduce those layers. Within the second half of the project, what we really focused on is doing trials at roll to roll and on our development coating lines, and be able to achieve layer quality that is on par with the current high volume process line. And this is really important, because when you start printing layers upon layers, each layer quality is critical in order to achieve your MEA. So you can look on the left-hand side, the different steps in terms of the different coatings that we've added. Your first pass, which will be your first catalyst layers, then you would see along the way, if you're looking carefully, on pass 3, you will start adding your membrane, you will start adding your support, and then when you have your final pass, you will start adding your final catalyst layer. And as you can see on the right-hand side, on the little SCM, you can see each of those layers together that form your CCM. This process is really critical in terms of your ink rheology, but also each drying step is really important. Each interfacial layer is really important. But as you can see, we were able to produce really good on par in terms of the quality to the type of MEAs that are being produced nowadays. Next slide, please. So the next part of the manufacturing process that we were looking at is what we call the edge protection. So this is the part that goes around the CCM in order to support it, but also to protect the edges when it comes to durability. And so what you have on the left-hand side is a demonstration of printing directly onto the membrane for your edge seals, and on the blue and black square, which is printing directly into a CCM using a different type of material. So we were able to demonstrate using inkjet that we were able to actually print that protection layers. Really, really important and really, really fast process. So we then looked at the development coating lines, and we were able to demonstrate patch coating at row to row. So therefore, you're only coating the area of your CCM that you need the catalyst from. And then the second process will be using inkjet to then print that protection layer. So the concept was demonstrated, but we have to be honest, our inkjet capabilities was not large enough to be able to demonstrate at stack level, but we were able to demonstrate it at the smaller 50 centimeters square. That technology is fully capable. Can I have the next slide, please? So in terms of the functional validation, which is effectively what we want, so the additive layer manufacturing, we actually did 2 full stack at NetStack, and we run those at Rainbow Stack. So we made MEAs within the same material set using the current high production volume CCMs versus the current ALM MEAs. And we did 1 first stack at just after the midterm, and then a second stack at month 30. And as you can see, the performance of those MEAs is perfectly on par with the materials that we can produce from the high volume line. So perfect functionality equivalence. We've also demonstrated the same accelerated stress test equivalence on our RH and OCV cycling process. So once again, do not pay too much attention for the actual power output. As I explained, this is the same material set that we've used for Inspire, which was able to achieve 1.5 watt/centimeter² at much higher current densities. Can I have the next slide, please? And the final part that I want to present today is, what does a line actually look like? What does a Mamma Mia printing line would actually look like? And that was really the significant output that we wanted out of this project. So INEA then took all the different printing concepts, all the different drying concepts that we had worked together, and developed the line for us, working out what the costing of those lines are. And as you can see, this is at the bottom what the line would look like. So this is a 40-meter length line, so 120 meters square footprint. And the cost would be 50 million for a 3 gigawatt per year production. And remember, this is modular. So in order to achieve your 10 gigawatt per year, you just add several lines in order to have your production. And this is also modular, which means that each modules can be actually taken out, and you can bring in a different printing technology through if something comes up as well. So this line is now ready to go. It's been all designed, and at Johnson Matthey, we are definitely looking forward to exploit this technology within our next factory. Next slide, please. So I have mentioned digital printing via inkjet a little bit within the start of the project. Now, the final output of the Mamma Mia project is not based on inkjet. The lines that you've just seen, all the layers that were printed, they were not using inkjet, bar the seal deposition. But we had big hopes for digital printing, and we still do. We think digital printing for fuel cell is the next big development. However, while it has been demonstrated in literature and demonstrated by ourselves as well, that you can make inkjet printed layers that are functional in terms of their electrochemistry, the print heads themselves do not have the durability to be used in a high volume process. Corrosion of those industrial print heads by the catalyst inks is very significant, and the lifetime is limited. Furthermore, the inks that we use, they're not readily usable. They all tend to foam a lot, and you need a very strong recycling system within your inkjet system to be able to use them. So inkjet is not yet ready for high volume. But as we had a look in the previous slide, our line is modular, which means that if we do have an inkjet print head that is durable, we could potentially remove that module that we have currently and put another module in order to use digital printing. And digital printing has a huge advantage because if you want to change the footprint of your MEA, it's a question of just dialing it in and present a huge advantage from a manufacturing standpoint. But what Mamiya has done, because we were printhead agnostics, we were able to actually talk to all the printhead manufacturers, and they all think that it is entirely technologically possible, and this is something that they should be looking at, and they're going to carry on working at that particular problem. So we managed to give all those manufacturers a set of specification. We were also provided with all their kits in order to assess the durability of their printheads. So we've gained a lot of knowledge, both ourselves, but also a lot of the printhead manufacturers. And finally, one bullet point that I often talk about is inline quality control. For the moment you start printing black on black at the type of speed that we are talking about, inline quality control is key. And this is where large difficulties start. So while in Mamiya we had a small task within a work package that was looking at this, we had very limited capabilities of looking at that problem particularly. And it is something that, as a challenge, I think the industry needs to look at going forward. Next slide, please. So in terms of exploitation, as I already mentioned, what Johnson Matthey is, systems intent is to start building inkjet within their portfolio in terms of being able to manufacture CCM-like products. INEA will be providing upgrade to existing manufacturing lines. And finally, all our academic partners will use the project output within their academic portfolio. And I think the impact is clear in terms of high volume, high speed coating, and also high utilization of material. Next slide, please. The other part that Mamiya has done very well is the synergies with other projects. So I've already mentioned the material set that we've used from Inspire, and we had also feedback with Gaia. We also had a lot of exchange of ideas with Feed for Amanda in terms of the characterization. We had a lot of feedback with Volumetric, which was doing a lot of raw-to-raw concept work. And finally, a project that only started is Camelot, which is looking at digital printing. So a lot of our digital printing experience we want to put to the fore within this other project. Next slide, please. The usual dissemination activities in terms of website, flyers, posters, conferences, and 4 publication papers. Next slide, please. And finally, I think the whole Mamiya team wants to thank you. It's always humbling to be there at the project review days, particularly when we know the type of reach that the project review days has. So I really, really want to thank you for your attention. And obviously, I want to thank the FCHDU or the Hydrogen Partnership for their support throughout this project. Thank you.
Thank you. Thank you very much, Sylvain, for your presentation and for covering a lot of things, which I believe your presentation already have answered some of the questions that we were getting in the Mentimeter. So thank you very much for that. I will still summarize 2 questions for you. There was one about, well, there are several manufacturing techniques for the CCM. Why did you choose this one? And did you research other options as well during the project, I believe?
Yeah, I mean, the first half of the project was effectively looking beyond the fuel cell industry, going to all the various different techniques. And we've actually published some of the papers in terms of some of our reviews of those techniques. The the bottom line is a lot of the roll-to-roll techniques currently requires you to print a first layer, and then you're going to need to unwind and print the second layer. And that is one of the biggest bottlenecks that you're going to have within your process. By having all printed MEAs, you remove all those intermediate steps and you're able to carry on at speed for your coating. Huge improvement in terms of capacity.
Okay, thank you. And then two very concrete questions. I will put them together. Hopefully that's fine. How did you prevent actually the different layers of the CCM from mixing when they were in a liquid state during the manufacturing? And then actually I will pass this one.
That is all the know-how. That is all the difficulty. More than just the layer drying and not mixing, you need to have some intermediate steps. But more than that is how do you avoid the solvent within your inks to be able to be removed from one layer before you move to the next. So really the key is what you do at those intermediate steps, and also what you do at those interfacial layers. So that is very much the key to the process. It is what makes the process work. It's those intermediate steps that is the critical part.
Okay, thank you. And then the question on the roll-to-roll process is: does it integrate a layer for the mechanical reinforcement of the membrane?
Well, the line design that you have seen on one of the last slides, yes, integrates the whole process.
Okay. And then final question now, I will put two. There was someone from the audience that was asking if you could elaborate on this 10 gigawatt per year demand. And it was, of course, a question to how many MEAs do you need for a light duty vehicle? That would be the question. I don't know if you can answer that.
Oh, I have it in the spreadsheet somewhere, but this is huge. I think you are talking several hundred millions of MEAs. But the key, I think, that we need to remember for fuel cell is, as a business case, a 15 million line for 3 gigawatt of output is small. If you compare that for battery, battery technology is an order of magnitude greater. You have to have a zero at the end of that process, if not 2 zeros, in order to have the same output. So in terms of the business case, those lines can be easily multiplied to reach whatever productions you need to produce. And for about 50 million, you end up with a manufacturing line able to produce that 10 gigawatt per year. And this is a relatively small risk if you look at the business case. It pays for itself very quickly. As an exploitation, this is something that is very clear.
Thank you, Sylvain. And I just to end that, I got that you said that yes, you are considering to use this production line in your new manufacturing. Correct. So I think that also answered one of the questions we had. Thank you so much. I'm afraid we don't have more time but I believe we answer, if not all, most of the questions. So thanks again, Sylvain.
Thank you.
And now, thanks. I'm glad to give the floor to John Pietras. He will be talking about the results of the project Oxygen, which was looking at the next generation of solid oxide fuel cell stack and hot box for stationary applications. So, John, the floor is yours, and thank you so much for joining us despite the time difference. Thank you.
No problem. Thank you for the introduction and the opportunity to present the results of the Oxygen project. As you said, my name is John Pietras, and I work for Saint-Gobain. And if you have more interest in the topic after the talk, we can talk via email, web chat, visit our website. So please, next slide, please. A quick overview of the project. This project actually started in 2017 as part of the Fuel Cell System Technologies programs. It just finished up this fall, ran about 3 million euros. And the project was a good consortium of 7 different groups led by Saint-Gobain, but involving CEA, Engie, Fraunhofer, IKTS, IFER, Ichicalde, and SINTEF. Next slide, please. The goal of the project was to have three main objectives. One was to define the specifications for a micro CHP for solid oxide fuel cells. And so in this case, we're specifically focused on European individual houses and small commercial facilities. We also wanted to then develop the technical platform, so not only a stack that's suitable to reach that market, but also a modular hotbox concept, because those different markets will utilize different size stacks and systems. Assess the performance, and then also look at the reasons for further improvements, and also look at the supply chain and the economic impact. And the schematic on the right-hand side, we see how we achieve this. We started with a generation 1 product, which came with a small stack, 150 watt stack that showed very good lifetime at 0.2% per 1,000 hours. That was measured over 10,000 hours. Along with that, we then moved into the program where Fraunhofer IKTS would take that stack and design a hot box around that and run through several learning loops along with our partner CEA and Ichicalde. At the same time, Angie looked at calculating some theoretical calculations that we'll look at in a minute to think about what the optimum stack size and hot box size are. And running along the baseline, our academic partners also looked at how to improve the stack performance, and then we integrated that into a next generation stack. Next slide, please. So now I'll talk about a few of the key achievements. One was looking at hot box size, and this is a very interesting work that was done, quite a detailed modeling here. I'll just briefly touch on the inputs, which were two, looking at buildings and the system itself. So by buildings, I mean, what is their use? Was it a single family or a multifamily house or a non-residential building? The market, so where the system was located, and then the characteristics of the building, such as its insulation value. On the system side, we looked at the characteristics of the system, such as the power output that it was designed for and the efficiency, electrical efficiency of the system, and also the management scheme in terms of the hot water temperatures and the tank size. The outputs were economic, looking at the energy bill, both for the electricity and the natural gas required in total to run the home or the building, and the total cost of ownership. And on the right-hand side, I show some examples of what we are looking at. But the major insight was the fact that the payback for these systems is really limited by the number of times the system has to stop throughout the year, and also the auto consumption ratio for the system. So the upper right-hand slide shows the number of stops per year as a function of system size and power output. And what you can see is that around 600 to 700 watts, we start to see times when the system has to stop. That's when we're producing too much heat. There's too much hot water for the system that can't be used by the building. And so the system actually has to shut down. And once you get above 1 kilowatt, it rises dramatically, regardless of the location of the system. Next to that, we see auto consumption. So this now is looking at the amount of energy that the home utilizes compared to the amount of energy that the system produces. So at low power outputs, of course, the home can consume all of its output. And then as you start getting a larger and larger size, the home just cannot utilize that power. So again, around 600 to 700 watts, we start to see a sharp decrease in the amount of auto consumption. So when you put these two things together, you really start to get a picture of how these stationary fuel cells should be sized. Next slide, please. So on the right-hand side, I show a schematic of how we then monetize that. So we're looking at across the x-axis, the size of the stack, and on the y-axis, the cost. So it's negative, meaning saving money. And the yellow line represents the cost just to own the system. So the larger the system is, the more it costs. And the difference between that and the amount of money saved, which is the orange line, gives you the green box where you're actually economically feasible to purchase the system and own it. And you see that there's a trade-off there at some point. Since you're not utilizing all the capabilities of the system, it's actually not economically advantageous to purchase the system. So this gives us now a good feel of how to size a system or a stack based on location and the type of building that you want to place it in. So if we summarize that, for single family houses, a power output of around 600 watts can fit for all the countries, a little bit less in Italy since they have more heat there. The power efficiency does contribute to how many times the system has to be turned off and on. So the more electrically efficient it is, the less heat that's generated. But it's not actually as big of a factor as you might think once you go through all these calculations. For multifamily homes, SOFC can be operated more efficiently all year long, and the power output of around 2 kilowatts can fit for all countries. And that market seems probably the easiest to address because of those two factors from a cost standpoint. And in the commercial sector, for retail, offices, and education, those are really tricky applications because you have to think about the fact that every weekend they're typically turned off and not used, those buildings. So it's probably not a great application for solid oxide fuel cell based micro CHP units. On the other hand, in the health and hotel sectors, they could be attractive as you get to larger systems above 5 kilowatts and at least 50% electrical efficiency. Next slide, please. So now we move from the economic calculations to design and building of the hot box itself. So along the bottom, I show some images of a 40 cell stack that was designed and built to reach that 600 watt mark. We did quite a bit of modeling at Fraunhofer IKTS, both to look at how the stack operates, its temperature, its output, stresses involved, and then designing a hot box for that size and scale. As I said, we went through multiple iterations of design in that to improve its durability, decrease its size, decrease its weight, built out the structure, put the stack inside, tested that, and then was able to even connect that with a simulated system at ICICALDE. So what we found was that we were able to operate the stack at 50% of its rated current, and that matched the output power from the simulation extremely well. The simulation shows that if we can reach an output of 300 milliamp per centimeter squared on the stack, we'd be able to hit that 600 watt target that the simulation showed would be a good economic standpoint. The gas feed system was demonstrated to be able to control the temperature swings and the gas compositions that we need to operate the stack as well. And then finally, the design, although here I show it with one stack inside, was designed to be scalable. So that way we could hit multiple markets, such as the 2 kilowatt class for the multifamily home. Next slide, please. So if we now drop down and look at material development, there was a lot of work done by SINTEF and IFER at the button cell level to improve the performance of the cells and then the stack themselves. On the left-hand side, I show work we did on the anode, and on the right-hand side on the electrolyte or the oxygen ion conduction. In both cases, we were looking at conductivity mainly. So on the anode side, you see we had a 50 times increase in conductivity. So that would definitely help improve the performance. And we also stabilized that conductivity. So the inset box there, it's quite small, but you can see a blue line that's increasing. That was the baseline resistance as a function of time. And the black line down at the bottom not only is much more conductive, but also much more stable. So that was a fantastic improvement. We also on the anode side wanted to look at simulating emergency shutdowns. So in this case, what I'm talking about is what happens when air is introduced to the anode side and we end up with a full oxidation of the anode. We want to make sure that the stack is stable against that. So we developed a very deep oxidation protocol, and that's been published and shared publicly. So it'd be good if people are interested, they can check that out and match against what we've done in the past. Once we did that testing, then we found nickel coarsening, and so we worked to reduce that. We were able to improve the redox stability marginally. And on the right-hand side, just to touch on this, we also looked at improving the electrical conductivity of the electrolyte phase. Here we had much more than what we planned to produce, so we did a great job improving the electrical conductivity of the electrolyte. And an important point I want to note here is that we're also able to match the co-sintering characteristics of the stack itself. It's a point I didn't mention in the slide above, but the Saint-Gobain design stack is a co-sintered system where both the anode, the electrolyte, the cathode, and the ceramic interconnect are all sintered in one co-sintering step. This is meant to reduce the number of thermal cycles that the stack has to go through during manufacturing and thus reduce stack cost. So that's great from a cost standpoint, but from a material standpoint, it puts a lot of constraints on how these materials behave during heating. And so it was a big accomplishment to be able to match the sintering profile of the electrolyte and the new anode to the rest of the stack. So if we go to the next slide, please, we'll show you the results as we integrate those new material sets into short stacks. So by a short stack here, I mean it has the same cross section as the full stack, an 8 by 8 centimeter square, but it was only 4 cells tall. On the right-hand side, we see the IV curve for that, and the line in green shows a slight performance improvement during integration of the new material sets in the Gen 3. But I think maybe one of the most important points is looking at the OCV. And we see that even though we were able to make new material sets, we're able to integrate those into the co-sintering process without any cracks, meaning the OCV looks very good and stable. Efficiency-wise, we're able to hit 50% efficiency in simulated reformate at 65% fuel utilization, and we hit the 300 milliamp per centimeter squared, which then tells us the output of the stack. The full stack would it be around 650 watts, again, right in the sweet spot of what we calculated based on modular sizes. If we go to the next slide, please. We also did some durability testing. So the short stack was tested for just under 3,000 hours under steady state operation, although we did change gas compositions during that time frame. So I just showed a snippet of that. We showed very good durability. In this particular snippet, it was running at 30% fuel utilization with a degradation rate of 0.36% per 1,000 hours per cell. Next slide, please. So exploitation and expected impact, quite a few, but I'll just touch on 2 that I think are important. Number 1 is the initial thing I talked about with the size of the stack and how that affects the economics of the situation. That was a public output. And so I encourage all of you to go check out that extensive paper written. And on the scientific side, there are upcoming presentations on the improvement of the electrolyte and the anode interconnect that you can look at upcoming scientific meetings. Next slide, please. So risk, challenges, and lessons. You see the team on the right, a very excellent team. We had technical and non-technical learnings. Maybe I focus on the non-technical side. Actually, we really segmented the project to allow the team to spread the tasks, and this allowed us to move very well along multiple fronts. But with that comes the challenge of drift. And so having strong communication between all the teams at a high frequency was critical. We were able to do that to overcome quite a few challenges that we had, and then also work together to solve problems. We had quite a few on-site team meetings. Then once COVID hit halfway through the project, we had to switch to virtual meetings as everyone else. And of course, we had a lot of learning on that side, but we did do a lot of learning. So that was good as well. And then finally, I want to touch on stability. It's very important for any project, I think, and we learned that quite a bit in here. Now, stability comes in many factors, including infrastructure, personnel, and production, and making sure we keep track of all those things. And if there's any changes, really being very careful to over-communicate to overcome those challenges is critical to success. And with that, I thank you again for the ability to present this project, and welcome any questions either here or offline.
Thank you. Thanks a lot, John. And very glad to have you present it, of course, on behalf of the consortium, but also as Saint-Gobain, because I think it's fair to say it's a new player in our projects. I mean, we have not had you in the past, so it's very nice to see new players coming into our projects as well. So thanks a lot for that. There are some questions. The first one would be very, very concrete and most of a clarification. If you could elaborate a bit on the degradation rate, I could not follow. If you could elaborate, I understand the values you gave at the end were on the short stack, but I could not pick on that clearly. Would you mind to double clarify on that?
Sure. Yes, the degradation rate that I showed you there was on the short stack. So that is a stack that is 8 by 8 centimeters square, 4 cells tall. And it was operated in multiple modes. So as I mentioned, the operational temperature was kept constant around 800 degrees. But what was changed were things like the fuel input, so different simulated reformates, and then also different fuel utilizations. The total time for the test was about 3,000 hours. Okay, perfect. And the average degradation rate was around 0.5% per 1,000 hours, but it depended on the exact composition of what was fed into the stack.
Okay. Thank you. And that brings me actually to the next question, which would be, what are your plans? I mean, are you planning to continue developing the stack? That would be one. And actually, an add-on to this question would be, is your stack switchable, or are you planning to look at reversible operation as well? Are you investigating basically electrolysis? So a bit of a mixed question there.
Yeah, great question. So in fact, as we are a new player, we're definitely continuing on and looking into all aspects of fuel cell operational mode, but you hit a key point, which is not only fuel cell operation, but reversible mode as well. And we've started down that path as well. We have multiple projects ongoing right now looking at straight SOEC operational mode and then also operational switching mode, as was discussed in previous points, that it's the same material set, and if we can improve those materials, we have a very nice situation there as well. So Saint-Gobain definitely looking to provide materials, so powder. So we're a large material powder supplier, inks as well. So that could be paste as well, subcomponents, stacks, all of the above.
And I guess when it becomes to integrating the system, you will be looking at joining with partners out there.
Exactly. So that was a key aspect of actually the project that we ran, is that we had pure research partners, we had industrial partners such as ourselves that make powders, make subcomponents, make stacks. We also had a system player, Ichi Calde, and we also had a gas supplier as in Anjay. So looking, collaborating across that entire value stream is extremely important, I think.
Okay. And just to end, because I know we are running a bit over time, but we had this technical break. You mentioned the challenges and you kind of covered that already, but do you have a feeling where you will head first, domestic sector or larger commercial applications? I don't know if that's something that you have come up with already, or is it still open in the air?
It's a little bit up in the air, but I will modify the answer by saying Saint-Gobain, one of our big strengths is being a component and material supplier. So building off of that base is probably the most critical aspect for us. So that means collaborating with other stack suppliers, developers to supply points like the powders at first. That allows us to increase the volume, bring the cost down for everyone. So that's probably the first area that we would look at it specifically.
I see. Thank you, John. Thanks a lot indeed for all your questions and thorough presentation, which indeed cover a lot of the points that were pointed as questions. So thanks a lot, John, for your contribution. And yeah, with that, I would like to close the panel, and I would definitely like to thank you very much to all the speakers, to Ang, Johan, Sylvain, and John. I found it very interesting myself, really nice and good opportunity to learn on the results of the projects that I've ended, but also on the progress of other ongoing projects. I invite the audience to, of course, follow up throughout the project websites if you have any other questions. And yeah, I want to thank everyone for your attention, and I wish you a very good rest of the day and a very good lunch to everyone. Thank you again to the speakers. Pleasure. Thank you. Bye.
Good afternoon, everybody, and welcome to this session of the program review days, which today now is going to be dedicated to early research on alternative routes of hydrogen production. My name is Claudio Pavel. I'm a project officer at Clean Hydrogen Partnership, and I will be your moderator for the next 1 hour and about 20 minutes. First of all, I would like to give you a flavor of what this session is about. Yesterday, we have learned about many results coming from our projects working on electrolyzers. So in this session, we are going to remain on the topic of hydrogen production, but moving this time to the production routes other than electrolysis. Today, we have with us 4 projects dealing with hydrogen production from different routes, as I said, from biomass, for instance, or biogas, such as the decomposition of methane. And here we are going to have 2 projects, Biorub Plus and 112 CO2, or using solar energy in the photoelectrochemical process. And here is about the PEXIS projects. And the last but not least, through water splitting using thermochemical cycles. And we're going to have with us the Hydrosol Beyond project. Before starting, let me kindly remind the audience to drop their questions in the chat box, if possible, directing them to one specific project. And the second point, I will kindly ask speakers to try to stay within maximum 15 minutes. So we may have the possibility to pick up some questions either after each presentation or at the end of the session. Having said that, let's start straight away with our first speaker, who is Massimiliano Antonini. He's a managing director at HySea Tech in Turin. And he will present the project Biorub Plus, dealing with advanced direct biogas fuel processor for robust and cost-effective decentralized hydrogen production. Buongiorno, Massimiliano. Please go ahead with your presentation. Thank you. Make sure that you are unmute, Massimiliano. Thank you.
Can you hear me now? Thank you, Claudio, and thank you to Hydrogen Europe to give this opportunity to present the outcome of this project. I'm going to present the results and the messages and the lesson learned from this project. The name is Biorub Plus, and the aim was the development of a very efficient way to get to green hydrogen starting from biogas as a renewable source. Next, please. I'm going to make this presentation also on behalf of the coordinator of the project, Professor Fino from Politecnico. Next, please. So the project started in 2016, and the overall budget was close to 4 million. Next, please. Here you can see the overall scheme of the project, of the plant, the demo plant that we have designed and built. Well, the main features of this process, which is based on a peculiar way of doing steam reforming from biogas, is the reactor itself. It's an oxidative steam reformer. That means that we get some help from some oxygen, and this is an interesting way to get rid of the issues like carbon deposition or total conversion of hydrocarbons. And the reactor itself was coming to a previous project. So we had a previous project giving us the possibility to focus on the oxidative, the reactor itself, on the core of the technology. And with Biorub Plus, we got to the implementation of the whole process, the whole chain. And the whole chain is completed by a purification module that was based on a specific PSA system. And let's say the heat management, which is for this kind of complex process, it's key. It's the key of the performance. So that was based on a steam drum and on a very innovative porous burner, able to get all the value, all the heating value from the tail gas we get from the purification of the reformate to get to pure hydrogen, and serving the different points of the process where we need to get excess heat and deliver the heat needed to properly condition the feeding to the reactor to assure stable and efficient operation. Next, please. Well, you can see a picture of the performance of the reactor itself. Next, please. I'm going to show you in the following slides some pictures of the main components. So you can see on the left the reactor, the oxidative steam reforming, coupled with the two reactors of water gas shift. You can see in the middle the hydrogen compressor, refrigerant compressor serving the PSA, and you can see on the right side the PSA that we have done for that. Next, please. Here is a table of the risk that we were considering at the beginning of the project. I have to tell you that the risk for pandemic was not considered, and that's unfortunately was an impact that was not considered at the beginning of the project, that was leading to delays and issues in being able to really operate the activities like installation and operation of the plant. Next, please. So we considered in the project how to basically get results over the project itself. And in this project, there were at least three interesting achievements which can have a life over the project. So we are talking about three specific components that in some way we can see a direct market application in hydrogen business, but not only in hydrogen business. Next, please. You can see here a picture which is summarizing the path that we have done on the core of the reactor, which is the porous catalytic support for the reactor itself, that was developed on a very small lab size, and then it was scaled up and put inside the reactor. Next, please. Here you can see the scale up of the reactor itself. So from very small scale, we got up to a size which is already, as we can consider later, is already a size which is interesting for this specific application, because biogas is not realized in sizes comparable to refineries, but typical size are starting from the actual flow rate that we were processing. So we are talking about 50 cubes per hour of biogas to process. Next, please. Here you can see some other pictures of the auxiliary components that we have designed and procured and built and installed to sustain the stable operation of the plant. So you can see air compressor, you can see the ejector, which is a feature that allow us to avoid another compressor. So in this way we save energy with that. I would say next, please. And here is a bigger picture with some more details of the core of the reactor, coupled together with the two water gas shifts reactors. Next, please. Yeah, this last picture is for what I was referring at the beginning as one of the key performance of the plant, which is the accurate collection of all the streams getting to potential waste heat. So in this concept, we are collecting all the heat that is available in order to deliver as much as possible the preconditioning for the feeding of the reactor. And that's, again, is the key to get to high efficiency, high overall efficiency of the product. Next. Yeah, you see here again the compressor for the hydrogen is a magnetic coupling compressor, which has to deal with very pure hydrogen, and then the PSA on the right. That was again developed on purpose with specific absorbent material to allow quick cycles, which is again the key to be efficient. Next. You can see here an overview picture of the site and the installed plant. You can see in front of the picture the flare and the other auxiliary system like nitrogen to inertize the plant and water softening and typical auxiliary system. Next. Well, we show here a reference composition of the biogas, even if in the reality the biogas composition is changing very frequently according to the kind of different feeding of the anaerobic digesters. And this plant was operated in a site which is dealing with urban waste anaerobic digestion. So we have tested the plant with one of the kind of biogas which is giving more trouble in the treatment, in the processing, because it's varying frequently in the composition, and also the pre-treatment is something which cannot be neglected. But also thanks to our past experience in dealing with biogas, that was properly managed. So again, the size of 50 cubes per meter per hour, cubic meter per hour of pure hydrogen is already a size which is very interesting for the potential market. Next, please. So we consider also in the project how this technology, this concept can have place in the market. So we were aware, and we analyzed the market potential, considering how hydrogen can be an energy vector more than a reagent for processes. And next, please. We focused on the evaluation, on a more detailed evaluation of the economics connected to two cases, two typical cases: the transportation, the use of hydrogen, the transportation, and the case of utilization of hydrogen into industry as a reagent, which is actually a real case happening already today. And I can show you the very interesting message that we got to in the next slide. So already in the size of the plant that we demonstrate, and in sizes which are slightly bigger than 50 cubes per hour, we can already today get to a price, to a production cost of the hydrogen, which is already very interesting compared to what we can achieve with other technologies, talking about electrolyzers. We can also easily see that with of course, 24-hour operation, we can achieve the best result in the economics, but this is pretty obvious. And the cost is of course really important, because I think that the demand, which is lacking at the moment, the real demand, can be stimulated if we can deliver today or tomorrow morning a cheap hydrogen, affordable hydrogen, being green, like the one coming from the biogas. But in the next slide, please, I think we have the most important message, because if we want to start with hydrogen, we have already today available a product, a technology that can be achievable with the cost, but what is most interesting is the comparison of the footprint. So we can see that because today we don't have 100% of green electrons in the network, grid, we have done the calculation using the energy mix as an average in Europe. The really impressive message is that today doing hydrogen, green hydrogen, starting from biogas, can lead to a footprint, to an impact of the overall CO2 emission, which is less than 1/4 of what we can achieve today with an electrolyzer. This is the last message of my presentation. I thank you for the attention, and I think this message is really important. It's to be considered, because if we want to start really with hydrogen, we have already a solution to start. Will not be the solution to solve all the issues and to serve all the demand, but it's for sure the way to start. Thank you.
Thank you very much, Massimiliano. Very interesting and to the point, and as well on time. I'm taking a few messages: the market potential, the interesting cost, as you said, for hydrogen, and until some questions may come on the chat box. I'm aware, because you mentioned many efforts from the consortium on developing and improving the reactor. I was wondering, what about the catalyst? Are you looking as well to find and to develop any innovative catalyst composition? And I think for the biogas reforming, the state-of-the-art catalysts are based on nickel, supported either by ceria or zirconia or alumina. So my question goes into the direction of the catalyst development, or if you have any issues with the stability under the operating conditions, eventually the scaling up, or either or not these are based on abundant natural resources.
Well, there was a quite important catalyst development carried on by several partners. Some of them very reputable in catalyst business. The development was focused not only on the catalyst recipe itself, but on the specific kind of support, being working into an oxidative steam reforming. So it's not like developing a catalyst for the steam reformer fed by biogas, but it's a different environment. And of course, the help of the oxygen is not negligible. So this is a way to get to an easier solution of the typical issues like carbon deposition. That is a way to decrease significantly the performance. And yeah, of course, the development was aiming to develop new catalysts, thinking mainly about stability on one side, but with the oxygen, life is easier. So aiming to reduce the cost and reduce the utilization of precious metals.
What about the composition itself of the catalyst?
Oh, well, I'm not so deep in that. I'm an engineer, managing director of the company. I I cannot give you the details of the recipes. What I can tell you is that there were different and several testing aiming to reduce the amount of precious metals.
Okay, I think it's a good answer at the end. Thank you very much, Massimiliano. I think at this point, I would like to invite the second speaker, who is Sonia Kalnan. She's a research project manager at Helmholtz-Zentrum in Berlin. And she will present PEXIS project, which deals with the technology and the demonstration of a technology at a large scale based on photoelectrochemical system for solar hydrogen production. Sonia, the floor is yours.
Thank you. My name is Sonia Kalnan, as has already been said by Mr. Pavel. And I'm here to present the PEXIS project to you, and this was dealing with the technology demonstration of a large-scale photoelectrochemical system for solar hydrogen production. Next, please. This project was made under the call topic for the development of processes for direct production of hydrogen from sunlight, and it started in January 2017 and ended in December 2020. And therefore it's completed. And the total budget was around 2.5 million, and it was fully financed by the FCH-JU. Next, please. There were several project partners. From Sweden, we had Uppsala University, which was dealing with material development of copper, indium, gallium, diselenide solar cells, and also material development of transition metal electrocatalysts. And then also in Sweden was Solibor Research AB, which was manufacturer of copper, indium, gallium, diselenide photovoltaic modules. And then in Germany, from Germany was the Helmholtz Center Berlin, where I'm from, and we coordinated the project, and we're also dealing with development of silicon heterojunction photovoltaic driven alkaline electrolysis, and also with transition metal based electrocatalysts. And then the Forschungszentrum Jülich was represented by actually two institutes. One of them was dealing with thin film silicon based photovoltaics and alkaline electrolysis. And the other was developing the PEM electrolyzer and the system development for the whole PV electrolysis. And then from Italy was Enel Green Power, which is mostly known as a utility for energy, but also it owns a factory for silicon heterojunction photovoltaic modules. And the CNR is a research center in Italy, which was looking at how to reduce the use of platinum group metals in PEM electrolyzers, and also looking at the effects of let's say low solar concentration using, for example, bifacial PV on the performance of solar photoelectrolysis. The next page, please. So there were several targets for the project where we had to show a hydrogen production rate higher than 16 grams per hour, a solar to hydrogen efficiency higher than 6%, device stability such that after half a year of operation that the initial efficiency had not reduced by more than 10%. And then there was a cost target of less than €5 per kilogram of hydrogen. And the targeted application and market area was mainly for decentralized hydrogen supply for residential settings or also small size commercial or industry use. Next, please. So I go to the main project achievement, which was the 10.5 meters squared demonstrator. So this was composed of silicon heterojunction modules, a group of arrays using silicon heterojunction modules, which you can see in the picture on the top, or on the left-hand side. So the silicon heterojunction modules are in the foreground, and in the background, they're copper indium gallium diselenide modules. So the combination of all these modules gave a total of 10.5 meters squared. What's different from the usual kind of photovoltaic driven electrolysis is that the PEM electrolyzer was directly hung onto the back of each module. I think you can see that in the picture on the right-hand side. And so this means that each PV module had an electrolyzer stuck to the back of it, and this kind of made a modular package. And so basically, if you have these, you can flexibly increase and or reduce the size of your array, of your system. So there were some balance of plant innovations that were developed at Jülich, mainly using just a water supply only from the cathode side of the PEM electrolyzer. And then also there was no active heating of the electrolyzer. So there was no, let's say, active also cooling of the electrolyzer. And additionally, also the water was not pumped, but it was just supplied by hydraulic means. So if we compare this result with what has been published in the past, we see that the 10.5 meters squared is somewhere an average size, and so is the total power of the system. If we look at the nominal power of the photovoltaic cells of around 1.73. However, the operation time was for more than 2,680 hours, which is the equivalent of the daylight hours in 8 months, and over the running in Jülich. And over that time, we had an average solar to hydrogen efficiency of around 10%. So this exceeded the 6% that was originally asked for. And as a result, also the rate of hydrogen production was 2.3 grams per hour per meter squared. So this compares quite well with the two other systems. One was in Saudi Arabia and the other one was in Japan, and where you can see definitely the solar to hydrogen efficiency is much higher in our case. And also the operation time demonstrated is several orders of magnitude higher. Next, please. So in the project, we not only looked at the technology that was shown in the demonstrator, but we also looked at several different approaches. And this was ranging from the technologies on the left-hand side with very high degree of integration between the photovoltaic and electrolysis components, but relatively low technical maturity, towards the right-hand side where we had less degree of integration, but highest technical maturity. So on the left-hand side, we have the thin film silicon, which was directly integrated with electrolysis. Basically, it was a monolithic system. And that was on a small scale of around 100 centimeters squared. Then moving to the second from the left, we had a copper indium gallium diselenide, also using alkaline cell, but in this case, the solar cell was removed, was somehow protected from the electrolyzer, but nevertheless, they were in thermal contact. And then in the middle, there was a larger system using silicon heterojunction cells with an area of 2,600 centimeters squared. And this was also with the thermal connection between the PV and the electrolyzer. And then lastly, the PV array, which you already saw in the previous slide. And then there was also an extra smaller system, which was looking at bifacial, the effects of bifacial irradiance on the cell. So next, please. So here you get to see the photographs of the systems that I showed in the previous slide, and we also have a comparison with other systems that have been reported in the literature. So the details of those systems or the references can be found in the paper in the bottom, that is cited in the bottom right of the page. And the graph there shows the solar to hydrogen efficiency and as a function against the solar collection area, basically the PV collection area. And ideally, we would all like to have, we'd like to be in the top right-hand corner of this graph. And you can see that the different devices that were developed in the project are at least closer to the right-hand side of the figure than to the left-hand side. And this shows really an advancement also for the general field, that we do have some devices that are really pushing towards attaining higher efficiency and also larger scale. So in the graph, you can see that there are some dots which are blue and some dots which are red. The blue dots are systems using non-platinum group catalysts. And then the red ones are showing the systems with platinum group catalysts. And again, you can see that also our devices, even for each class, whether with the platinum catalyst or without platinum catalyst, that we're at least almost higher than what is reported in the literature for the same size of devices. Next, please. So as a result of this, of course, I couldn't show everything. We attended over 20 conferences and workshops to present our results. We held a project workshop. Unfortunately, it also, because of the COVID pandemic, it was virtual. And then there've been 22 peer-reviewed publications, and there are 4 project videos. And the results of the project are summarized in the paper that's shown below. And then there are also public deliverables and videos of the project available on the project website. Next, please. Thank you all, and we thank the FCHJU and the European Union for funding the project.
Thank you very much, Sonia. Very interesting project, and indeed I had the pleasure to follow up towards the end of this project. I remember last year. Let's go directly with one of the questions from the audience now, which says, if when we're looking at the future large-scale photoelectrochemical hydrogen production, will there any cost advantages versus the standard combi PV and electrolyzers?
It depends on the settings. For really small systems, maybe the extra cost of having power electronics and also active thermal management of the electrolyzer it makes a very big cost in the whole system if the system is quite small. So I think in such as for smaller systems, this is why our target is really for residential and small industrial systems. It could be economical. And especially if it's been, if the system has been sized, if the PV and the electrolyzer have been sized according to the local climatic conditions. I think this is possible.
Another question comes again from the audience regards the cost this time, and says that the target of the hydrogen is around to have €5 per kilogram hydrogen. So what would be the cost reduction in the future? And I think the question relates to the technology developed within the PEXIS. Yes,
exactly. We did techno-economic analysis. Unfortunately, the results are not public because of some IP information, especially on the photovoltaics manufacturing side. But in that, it depends on the location. For example, that system that we demonstrated on the roof, if you take it to Catania and run it for 20 years, you achieve around 5.1 euros per kilogram of hydrogen. And that's also including the compression to 25 bar. But if you take this system back to Jülich and calculate, then it's 7 euros per kilogram. And we did a sensitivity analysis, and really the main thing that is required to reduce the price is the efficiency. So we still need further improvements in the efficiency, both of the PV module and of the electrolyzer.
Very clear. And the last point from my side, I remember that, you look at different concepts within the project, and as far as I remember, it was the thermally integrated approach. And this concept show even a better, higher solar to hydrogen efficiency compared to the thermally isolated devices. But yes. I remember the consortium at that time faced some difficulties on scaling up. I don't know if you can share with us some of the lessons learned, and if you have any recommendation for the scientific community to solve such problems.
Basically at Helmholtz, after the project ended at Helmholtz, we continued further developing the silicon heterojunction to alkaline system that is also in thermal integration, and there it's really just improving the how you connect the heat exchange system, how you design the heat exchange system. Yeah, basically that's the main thing. And of course, if you work in a hotter climate, you get more benefits than if you work in a cooler climate.
Great. Thank you, Sonia, so much. I propose to move further. The time is running, and to move to the third project, I'm inviting at this point Susanna Lorentzou. She's a senior researcher at the Center for Research and Technology in Hellas in Greece, and she will present Hydrosol Beyond projects dealing with the thermochemical hydrogen production in a solar structure reactor, facing the challenges and beyond. Susanna, the floor is yours. Thank you.
Thank you for the introduction. We can move forward to the next slide. So the Hydrosol Beyond project has started in January 2019. It's currently near the end of its third year. However, an extension of its end date was granted, so it will end at the end of 2023. The partnership of the project consists of 8 partners from Greece, which is the coordinator, the Aerosol and Particle Technology Laboratory of the Center for Research and Technology Hellas. From Germany, DLR. From the Netherlands, Hygear. From Spain, we have CIEMAT and Abengoa. From France, SEA. And from Switzerland, we have ENSISR and SUBSE. To give you some idea of the project, I will describe it in the next slide. Thank you. Well, the Hydrosol Beyond project is the continuation of a series of Hydrosol projects that dealt with the production of solar hydrogen based on a technology of structured reactors that consist of redox metal oxides. The target was to produce hydrogen from the splitting of water based on two-step thermochemical cycles. In the first step, we have the thermal reduction of the material, the metal oxide. And in the second step, we have the splitting of water on the reduced metal oxide and the production of hydrogen. Now, in the past, the technology was demonstrated on a solar platform, and it was the largest plant that was demonstrated for the specific technology. But currently, the project, the Hydrosol Beyond project, is dealing with the challenges that were identified in these previous projects, which can all focus on the improvement of the efficiency of the technology. So the efficiency of the process is very low, and we target in increasing the efficiency up to 10% by recovering the heat from the very high temperature streams that are produced in the process. We also will try to reduce the consumption of inert gas that is mainly used for the reduction of the material, the metal oxide. And we will also try to revisit the reactor design. Next slide, please. Now, moving on to the activities of the project, I have selected three main activities. In the first case, target of the project is to again investigate the structured materials. So in the past, there has been a lot of work on the materials and the investigation of structures, different structures, mainly monoliths and foams, that indicated how important the contact of steam with the metal oxide is to produce hydrogen. So in the past, honeycombs, honeycomb monoliths and foam structures were developed and tested, and the highest number of cycles that were achieved for hydrogen production were 600. In the current project, our target is to develop 3D ceramic lattices that consist of the metal oxides, the active metal oxides, and test them for over 1,000 cycles. Now, this activity is currently at an still at an early stage, mainly due to some delays that were related to restrictions in technical works. And but now we have new lattice structures developed, manufactured, and ready to be tested at our laboratory rig. We will adapt a fast agent protocol for the testing of these structures in order to accelerate their assessment and to simulate the rapid changes in the temperature that are happening during the solar irradiation of such reactors on the solar platform. The next activity that we are investigating is presented in the next slide, which deals with probably the most important part of this process, which is the recovery of heat. The target in the current project is to achieve over 50% of heat recovery. And the consortium investigates the development of a heat exchanger to recover the heat from the high temperature streams. It is a hybrid heat exchanger consisting of metallic and ceramic parts. And a lot of modeling and simulation work has been done. And this provided technical specifications for the manufacturing first of a small-scale prototype, which is already at our laboratory and will be tested, will be integrated in a laboratory rig for testing. And the other concept that is investigated is the reduction of the inert gas, which, as I previously mentioned, is used for the thermal reduction of the metal oxide. So in this case, we are trying to minimize the consumption of nitrogen. And we do this with three approaches. In the first approach, we will try to reduce the flow rate of the nitrogen that we use in the reduction step, and investigate the long-term effect that this reduction will have on the activity of the metal oxide, because the reduction, the regeneration of the metal oxide is directly related to its activity for hydrogen production and water splitting. So we need to see if reducing the rate, the flow rate of nitrogen will affect the activity of the metal oxide and its performance for hydrogen production in the long term. The other two approaches that we use, we would like to investigate, are the purification of nitrogen in order to recycle it. And the first approach, the first solution that is proposed in the current project is vacuum swing adsorption to remove the oxygen from nitrogen and recycle it. And the other approach, so the other solution that we are investigating is the use of another redox material to remove the oxygen which is included in the nitrogen stream. Now, these two approaches will be tested at the laboratory scale, while the first approach with a reduction of the nitrogen flow rate will reach the solar platform scale. Moving on to the next slide, the optimum target of the project, the ultimate target of the project is to increase its efficiency, and this will not only be done by revisiting and redesigning the solar reactor or integrating critical components in the system to improve the performance and the process performance, but also through smart control strategies. For example, that would allow an optimization of the selection of the most appropriate group of heliostats that would provide best irradiation of the solar reactors, as well as better control of and development of algorithms for the best control of different process modes and different operational modes. The target is to reach a 10% efficiency at the lab scale and a 5% efficiency, which is the state of the art for such kind of processes, the solar thermochemical processes, at the solar field tests. In the next slide, I am summarizing some of the risks and challenges that have been identified from the beginning of the project, and also having experience from the previous projects. The risks and the challenges have to do both with the development and testing of critical components of the process, as well as in achieving the targets that were set in the project, and especially regarding the efficiency. And the mitigation measures that we see could provide some solutions in case of those challenges. Would be adaptation of new protocols and utilization of conventional approaches that would, however, give acceptable results and acceptable performance. And also downgrading to lower scales in order to produce results that either in simulated environments, to produce results that would prove the effectiveness of the proposed solutions and the feasibility of the values that we target in the current project. With respect to the exploitation and the impact of the project in the next slide, we have used the service of Horizon Results Booster Team to better address the potential exploitable results of the project and develop in the best way the exploitation plan of the project. And considering a successful development of the Hydrosol Beyond and successful achievements through the project, at the end, we expect that it could have a major impact and provide better the socioeconomic scale, because we expect that producing solar hydrogen from water splitting would give the ability to store solar energy in the short term, long term, or seasonally to a clean chemical. However, to increase the impact of the project, we need to attract major stakeholders and experts, and also attract young researchers and skilled personnel, both within the current consortium as well as outside of our partnership. Moving on to the publicity and the dissemination activities of the project in the next slide. I give a list of publications and public deliverables that were done until in the first period of the project, as well as participation in some conferences and workshops, while the project tries to communicate its activities in the next slide through its website and its accounts in different social media. This is from me. I would like to thank you for listening.
We are thanking to you, Susanna. Thank you very much for this very interesting presentation. And just for the audience, so Hydrosol Beyond is very ambitious project, and if this technology is going to be successfully demonstrated at the large plant in Almeria of 750 kilowatt, is going to be, from what I know, the first large-scale solar thermochemical hydrogen production in the world. So we see it as very, very big achievement. Just a question came up in the chat. As the process works with the vapor, can it be used directly with salt water through evaporation?
Of course, the process utilizes water, but of course, when it is evaporated, it is clean, so any particles or salt is removed. So I don't see why salty water could not be used.
And yeah, many things to be done. I understand the ambitious goal to get up to 10% efficiency, and there are already in place some ideas through the recovering the heat. And we know that you were already developed this innovative heat exchanger operating at higher temperature, which is very interesting. To reduce the consumption of the inert gas and improve the reactor design. Susanna, we're looking forward, and best of luck to the project to become the pioneer in this field after so many years of research and testing. Thank you. Very much again. So at this point, I would like to introduce our four speakers, Adelio Mendes, who is professor at the Faculty of Engineering of the University of Porto, and he will present to us 112 CO2 projects dealing with the low temperature catalytic methane decomposition for COX-free hydrogen production by transforming the methane into solid carbon and clean hydrogen through so-called methane pyrolysis. Actually, this project, 112 CO2, is a special guest in our PRD, as it's supported by the European Innovation Council. So welcome in our program review days. And maybe before starting your presentation, Adelio, I don't know if you can tell us a bit about the acronym of the project. Why you pick up, what does it mean, 112 CO2? Thank you, the floor is yours.
Thank you for the kind presentation, and good afternoon to everyone. So the name is the emergency number for Europe. So we have an emergency concerning carbon dioxide, and so we found that it could be a good idea to name the project according to this number. Thank you. So yes, next this slide. So this project started last year, in September last year, and it has a budget of 3.6 million euros, all supported by the European Commission. It involves 7 partners from 4 countries. So maybe next slide, please. Thank you. So the countries are Portugal, where I'm coming from the University of Porto, and also the spin-off company Pixel Voltaic. From Switzerland, we have EPFL Lausanne, and we have Quantis. And from Spain, we do have CSIC from Valencia, and finally from Germany we have DRL. So this is a project, a FET proactive project. Next slide, please. Yes. So the organization of the project, it's pretty conventional. We have the research tasks. We have 3 main research tasks, which concerns, this is the composition of methane, so transforming methane in carbon and hydrogen, also known as pyrolysis. Actually, normally, German scientists, they call it pyrolysis, but mostly is known as decomposition. It's the same thing, doesn't matter. But the project targets the catalyst. So this is a project on low temperature methane decomposition, membranes, so proton conducting ceramic membranes for purifying the produced hydrogen, and the device itself. And Also concerning, we have a task on demonstration and a task on simulation. So please, next slide. Yep, next. So this is the reaction. So we have here the reaction is methane to produce carbon and nitrogen. It's an endothermic reaction. It's not very endothermic, but still endothermic. So the beauty of this reaction is if you use it with natural gas, you can produce hydrogen without producing carbon dioxide. But if you use as a feedstock, if you use biomethane, you are actually removing carbon dioxide from the atmosphere. And the beauty of this reaction is you can remove carbon dioxide from the atmosphere. You can produce useful hydrogen and useful carbon and make money out of this. This is the beautiful. So people are naming hydrogen according to the process. So you have green hydrogen when you produce no carbon dioxide. So someone named this hydrogen from methane composition of natural gas turquoise. But I think from biomethane, we call it bright hydrogen because we have 3 projects at once. We remove carbon dioxide from the atmosphere and mimicking the nature, we produce hydrogen and we produce a very useful product also, which is carbon. So next slide, please. So here we list the main advantages. So this is a 0 carbon dioxide emission process for producing hydrogen. It's cost competitive. Uses the infrastructure that we do have. So it will allow a very swift, very rapid change for this technology. And because this is a catalytic process we are using, it allows on-site and also on-board production. So you can, it's not for cars probably, but you know, for ships, for trains, for big trucks, it allows to produce on-site hydrogen from methane. So you can avoid all the problems that hydrogen you have concerning storage and transportation. And as mentioned before, we can remove carbon dioxide from the atmosphere at competitive prices if we use biogas. So maybe we can move on. Yeah, thank you. So is this project new? The idea of methane composition is around for already some time. So in Australia, we have this company, Azer. They were the first to start with a reactor that they use is a fluidized reactor, very small particles of iron ore as a kind of catalyst for transforming methane in carbon and hydrogen. So carbon coats these iron ore particles, which at the end you can remove this carbon from the catalyst particles. The process runs at 900 degrees. More recently, BASF disclosed a very interesting process, which is coal particles in a reactor running at 1,400 degrees. Sorry for the mistake. It's 1,400 degrees. It's a very, very high temperature. And the carbon that is being formed coats the coal particles that at the end you can dispose of or somehow recycle them. So next slide, please. Yeah. Next. Okay. So everything starts with the idea of using catalysts, because catalysts, they can allow us to run this reaction at much lower temperatures, say around 500 degrees, 550 degrees. But these catalysts are known to deactivate very quickly. How to go around that? So we propose two things. First, when the catalyst gets encapsulated with carbon, we just reverse the reaction. And since this is a reaction at this temperature that is 100% selective, it's an amazing reaction, you can detach the carbon from the surface of the catalyst. The other problem is sometimes this carbon is going out, not from to outside the catalyst, but actually to the bottom of the catalyst, where the catalyst attached to the support. And so they remove the catalyst. We also address this. So now we are really in the way to develop a very stable, very active catalyst. Next slide, please. The project is made of 4 main, let's say, technical or scientific work package. The catalyst, then this is an equilibrium reaction, so we have to remove actively hydrogen from the reaction medium. We address this using proton-conducting ceramic membranes, the reactor itself, and then a prototype for demonstration. Next slide, please. Well, concerning the catalysts, our target was about 0.45 grams of hydrogen per gram of catalyst per hour. Right now we are 3.6, so more than double. That was our target, the original target. So now we are really producing or developing very active catalysts. Next slide, please. This is the membranes, the proton conducting membranes, ceramic membranes. We can either, using these membranes, actively remove hydrogen using power, so electrical power, or just concentration difference. There are other concepts around that are also being investigated. This is probably the most promising. These membranes are stable at the reaction temperature. So next slide, please. And here we have a sample of some results from the methane composition. You can see the flakes of carbon that are detached after using the reverse reaction to remove this cap from the catalyst surface. Next slide, please. We have these 4 technical work package. Now we have 3 more, as mentioned before. Demonstrative prototype will start soon, not now, and then we are doing a life cycle assessment of this process. Is very, very important to understand how it compares to other more conventional processes. And we also target to build up an interdisciplinary community. We will see in a minute this. Next slide, please. Okay, exploitation plan. So we are patenting. So we have 1 patent. Now we will soon file a 2nd patent. Other patents will happen because this is really a process that is very desired by companies. So several companies are now contacting us concerning this process. So it's a process with a very high public visibility on this respect. Next slide, please. This project call also considers budget for third parties. So we soon open tenders for small projects innovative over the main project, and also 3 grants. Next slide, please. Okay, just summarizing the results of this project. As said before, this hydrogen is very, very important, because when you are producing green hydrogen out of electrolysis, the green electricity is not very stable in time. And since hydrogen is very difficult to store, you may want to use this hydrogen to produce synthetic fuels or feedstocks. And for that, you need a continuous flow of hydrogen. You cannot go up and down. You cannot use photovoltaic electricity and so shut down the electrolyzers at night. For the electrolyzer point of view, this is possible, but for the whole process involving the synthetic fuels and other products that are derived from hydrogen, this is not possible. So if we have this process, the methane composition from natural gas or from biogas, we will be able to have a continuous, constant supply of hydrogen to these processes. Second, this is a low-cost hydrogen. This is also a process that allows you to remove carbon dioxide from the atmosphere at extremely low costs. I remember the target for 2050 for removing carbon dioxide from the atmosphere is 150 euros per ton. This is far cheaper. And then carbon is very useful for the construction industry, is for coating the roads, for electrodes, for electrochemical devices. So you can valorize the subproduct. Next slide, please. Well, the results so far arrived. So we have now a reactor that delivers about 10 kilowatt per liter, with very high energy density, runs between 5 and 550 degrees C, no byproducts other than carbon, and is compatible with mobility. The catalyst is an engineered catalyst, so it's something more sophisticated. So we are learning more, we are putting science on this. And the catalyst support in the reactor is also novel. And it's a very stable operation, so no more 40 hours of operation and then deactivation. It goes beyond that. Finally, we have a spin-off, a company involved, which makes us very proud. Next slide, please. And so I'd like again to acknowledge the financial support by the European Commission that is making this project possible. Thank you.
Thank you very much, Adelio. On the cost, just a question right from the audience, which says that for the blue hydrogen, about 3.5 kilograms natural gas per kilogram of hydrogen, this is the need. And the question relates how much natural gas per kilogram of hydrogen will be needed for this turquoise hydrogen. Because from the stoichiometry, this may be a kind of 4 kilograms of natural gas per kilogram of hydrogen. So the question is, where is the advantage compared with the steam methane reforming, as well take into account the additional hydrogen coming from the water decomposition?
Thank you for the question. Let me see if I understand. So methane, the steam reforming, if it's from natural gas, produces carbon dioxide, which you have to pay today at 77 euros per kilogram, per ton, sorry. If it is from biogas, our process is removing carbon dioxide from the atmosphere, so it's more competitive. Finally, the steam reforming is an endothermic reaction. It's strongly endothermic. It runs at very, very high temperatures, so around 700 degrees, 600, 700 degrees. Here is a lower temperature. And at the end, you can heat your reactor from the methane composition using electrical systems. If you do so, you produce about 30% less hydrogen per kilogram of methane than the steam reforming. So the difference is not so high, but benefits are far higher.
It's clear. You already mentioned about the problem with the coke deposition on the catalyst surface, and you said that you reverse the reaction and you get regeneration back of the catalyst. I was wondering how efficient is this cycling regeneration? Are we able to get back fully the catalyst performance after each cycle, or how it goes?
This is ongoing development, but we conclude that we can regenerate 100%. So it's really fantastic thing. So the only problem we are now facing is some of the catalytic particles are detaching. We know how to prevent that, but we still improving the process. So this is the problem. So it's very, very effective, the process of reversing the reaction. And we are spending about 5 to 10% of the produced hydrogen for reversing the reaction and removing the carbon. So our target is 5%.
Yeah. Thank you very much again. Now we have just 5 minutes till the end, and I was wondering if you can make a round table right now and touch maybe a more general question regarding why research is important for developing such technologies for hydrogen production other than electrolysis. As you know, we have several electrolyzers on the market which are ready to achieve a certain technological and economical maturity ready for the commercialization. And maybe you can integrate in 1 minute answer, what would be the main end-use application for such alternative routes in medium or long term? So I would like to start with academia at this point and back to Adelio, maybe very short, very quick answer if it's possible.
Methane composition has 2 great advantages. First is dispatchable, so you can combine synergetically with the green hydrogen to make hydrogen dispatchable. And it's the only technology that I know that is able to remove carbon dioxide from the atmosphere at very low costs.
Susanna.
Well,
the same question, why
yes.
we should invest in research project?
Well, in the case of solar energy and projects that deal with the storage of solar energy in a chemical or a valuable chemical such as hydrogen, an energy carrier, research is very important because there are applications that are more mature, but there are also applications and technologies that are really in the early stage, although there has been research for several years done in these fields. For example, in the case of solar thermal plants, we have solar thermal plants producing energy, electricity, but we can combine solar plants with technology that produces chemicals and close the loop and close the gaps that a more mature technology has.
Thank you. Sonia?
Thanks. I would add on to what Susanna has just said. Indeed, the hydrogen electrolysis also driven by, let's say, photoelectrochemical systems or maybe photovoltaic integrated electrolysis is an alternative to, let's say, a big PV arrays with megawatt, almost gigawatt plants for electrolysis, because in the next decades, there's going to be a very high demand for green hydrogen. And I think the smaller users will not be able to access this, because the big industries do need quite a lot of hydrogen. And every solution, I think, at the moment has to be looked at to achieve the climate goals.
Great, thank you. And the last but not least, Massimiliano.
Thank you. Well, my main concern is that we are putting all the effort to develop solutions towards the environment, to mitigate the issue we have. But since we only have almost 30% of green electrons, the electrolyzer, the main model, the mainstream model of PV and electrolyzer, or whatever kind of renewables, green electrons and electrolyzers, that kind of model is just getting to increasing the overall emission of CO2 today, compared to the traditional steam reforming of natural gas, which is not renewable. This is a paradox. No? With the electrolyzer, we are getting to more or less double the emissions of a steam reformer based on natural gas. And on the other side, there is also the economics, which is the key to move something in the market. So we really need to find ways to start, because the model of the electrolyzer, after decades of research, I'm convinced that can achieve, together with the increase of the availability of renewables, it will achieve the target. But if we do not start, the market will not be stimulated and there will not be any demand. So we need cheap solution to achieve an affordable hydrogen, which is also beneficial for the environment. So I think that the project that were presented in this session are really aiming to that, because if we do not start, we will never achieve the target.
Clear. I think, I enjoyed this session very much, and I hope as well the audience enjoyed. It's clear that the research on alternative routes for hydrogen production is important, and it's going to be even more relevant, at least in medium term. So allow me to thank you very much, all our speakers today. Again, I think it was a very interesting session. Now we are approaching the end of the session. It's not the end of the program review days, and after a short break, we'll be focusing on research opportunities for hydrogen application in the defense sector. So having said that, I would like to thank and to close this session. Looking forward for other achievements maybe next year. Thank you. Have a good day.
Thank you.